Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're drifting into one of the smallest and strangest rooms in the universe, a room so tiny that no ordinary microscope could ever enter it, and yet it is the room from which almost everything familiar is built. The chair beneath you, the pillow near your head, the water in your glass, the air moving quietly in and out of your lungs, the bones in your hands, the stars above the clouds, and the old planet turning gently beneath us all are made largely from atoms. And at the heart of those atoms are particles called protons and neutrons. And protons and neutrons belong to a family with a rather curious name. They are baryons. Now, baryon is not a word most people use while making breakfast. You rarely hear someone say, "Good morning, could you pass the toast? And by the way, I have been thinking about baryonic matter." Though if you do hear that at breakfast, you may be in excellent company, or possibly at a very unusual hotel. But baryons are everywhere. They are not exotic in the sense of being rare. They are exotic in the sense that they are deeply strange once you look closely. They make up the heavy centres of atoms. They give ordinary matter much of its mass. They are part of the reason chemistry exists, why planets can be solid, why stars can burn, and why your hand does not simply fade into a mist of pure mathematics when you reach for a cup of tea. So tonight, our question is simple to ask, but not simple to answer. What is a baryon really made of? Not just in the schoolbook sense, where we say it is made of smaller particles and then move briskly along before anyone asks too many questions. I mean, what is really going on inside? What fills the interior of a proton? What keeps it from flying apart? Why is it heavy? Why does it behave as one particle if it contains others? And why, when physicists try to describe what is happening in there, do they end up speaking not of little balls glued together but of fields, forces, energy, motion, and a kind of restless microscopic storm? Before we wander into that small storm, let me ask you gently, where are you listening from tonight? Are you tucked away in a quiet room, with the lights low and the world settling down outside? Are you travelling, resting, studying, or simply letting your thoughts soften after a long day? And when you look around your little corner of the world, what ordinary object is nearest to you right now? A blanket, a phone, a mug, a book, perhaps a very patient cat. Whatever it is built from atoms, and hidden inside those atoms are baryons, holding together quietly without complaint, doing the difficult work of being matter. If you find this kind of journey soothing, interesting, or just a pleasant way to let the mind loosen its grip on the day, I would be ever so grateful if you gave the video a like and perhaps subscribed. It helps this small corner of calm science reach other curious people who may also enjoy drifting through the universe at a gentle pace. And if this question keeps you awake for a little while, well, at least you will be awake in good company, thinking about the inside of a proton, which is quite a respectable reason to miss a few minutes of sleep. So settle in, let the day become a little quieter, and let us begin with the familiar before we move toward the strange. Most of us first meet matter as something solid, dependable, and almost stubborn. A stone feels solid. A wooden table feels solid. A spoon has edges. A glass has weight. The world seems made of things that stay where they are unless pushed, lifted, dropped, melted, or accidentally knocked off a counter with an elbow. For most of human history, that was enough. Matter was simply matter. Earth, water, air, fire, metals, wood, flesh, dust, bread, bone. The world was full of substances, and each substance had its own character. Then, over centuries, people began asking whether the variety of the world could be explained by smaller ingredients. Perhaps matter was not continuous. Perhaps it came in tiny pieces. The idea of atoms is very old, but the scientific picture of atoms took a long time to mature. Eventually, experiments showed that substances really are made from atoms, and atoms are much smaller than anything we can see directly. Then came the next surprise. Atoms were not solid little beads. They had structure. They contained light, negatively charged particles moving around a much smaller, heavier centre. That centre was the nucleus. The nucleus is where our story begins to narrow. An atom is already small enough to defeat imagination, but its nucleus is far smaller still. If the atom were enlarged to the size of a quiet cathedral, the nucleus might be like a tiny dense object near the centre, with the rest mostly open space. This picture is not perfect, because the quantum world does not behave like miniature furniture arranged in empty rooms, but it gives a useful feeling for how concentrated the nucleus is. Nearly all the mass of an atom is packed into that central region. The soft chemical personality of the atom, how it bonds, reacts and joins with others, depends mostly on its outer electrons. But the weight, the sturdy presence, the heavy identity of the atom comes mainly from the nucleus. Inside that nucleus, for most ordinary atoms, are protons and neutrons. The proton carries positive electric charge. The neutron carries no electric charge overall. Together they form the dense core of matter. A hydrogen atom has one proton at its centre. Carbon has more. Oxygen has more still. Iron, gold, uranium, all the familiar elements have nuclei built from combinations of protons and neutrons. Change the number of protons and you change the element. Change the number of neutrons and you change the isotope. It is a quiet rule book from which chemistry gets its cast of characters. For a while, protons and neutrons seemed like fundamental particles. They were treated as basic building blocks, the heavy pieces at the heart of atoms. But physics has a habit of treating our simplest answers as temporary resting places. Each time we say, here is the basic thing, nature eventually raises an eyebrow and reveals a smaller or deeper level underneath. The atom was once thought indivisible. Then the atom opened. The nucleus was once treated as a compact object. Then the nucleus opened. The proton and neutron were once treated as elementary. Then they too began to show signs of inner life. Those signs came from experiments that did not gently peek inside matter, because there is no tiny trapdoor on a proton marked "Please open here." Instead, physicists used collisions. They fired particles at other particles and watched what happened. This may sound crude, a little like understanding a clock by throwing another clock at it. But in the subatomic world, collisions are one of the most precise tools we have. If you want to know what something is made of, you probe it with something small enough and energetic enough to notice its inner structure. The way particles scatter after a collision can reveal whether the target is smooth or lumpy, simple or composite. When physicists scattered electrons off protons at high energies, they found that protons did not behave like featureless points. Something inside them seemed to be carrying the impact. There were smaller constituents within. These constituents came to be understood as quarks. The proton was no longer a single indivisible bead. It was a composite particle. The neutron was composite too, and both belonged to a broader category of particles made from quarks. That category is called baryons. The word baryon comes from a root meaning heavy, and that name made sense when these particles were first being classified. Compared with lighter particles such as electrons, baryons are heavy, but the name also carries a slightly misleading comfort. It makes baryons sound like heavy little pellets, perhaps simple, compact, and understandable once you know what sits inside them. But a baryon is not like a fruit with 3 seeds tucked neatly in the middle. It is not a tiny bag containing 3 polished marbles. It is not a miniature solar system with little objects calmly orbiting a centre. Those pictures may help at first, but they begin to fail very quickly. A baryon, in the modern view, is a particle made of 3 main quarks, bound together by the strong force, with a great deal of activity surrounding and connecting them. That sounds straightforward until you ask what bound together really means. In everyday life, things bind together with glue, nails, thread, pressure, friction, magnets, or perhaps sheer determination if you're assembling furniture without the instructions. In a baryon, the binding is carried by the strong interaction, one of the fundamental forces of nature. It is much stronger than electromagnetism at the scale of atomic nuclei, and without it, protons and neutrons could not exist as stable particles. The atomic nucleus would not hold together, stars would not shine as they do, chemistry would lose its foundation. The universe would be a much thinner, simpler, less hospitable place. But the strong force does not behave like an ordinary force. It is not simply a tug between two little beads. It is described by a field theory in which quarks interact by exchanging particles called gluons. The name gluon is charmingly direct, almost suspiciously direct. It sounds as if someone looked at the job, holding quarks together, and said, "Well, there we are, gluons." But gluons are not glue in the household sense. They are particles of the strong field, and they themselves carry the kind of charge associated with the strong force. That means gluons do something photons do not do in ordinary electromagnetism. They interact with each other. The force carriers are also participants. The result is not a clean, simple pull, but a dense and active system. Here is where the inside of a baryon becomes especially strange. A proton is often introduced as being made of 2 up quarks and 1 down quark. A neutron is often introduced as being made of 1 up quark and 2 down quarks. This is a useful first description, and we will use it carefully. But if you imagine only those 3 quarks sitting still inside an empty proton, you are missing most of the story. The 3 main quarks, often called valence quarks, help define the identity of the baryon. They set important properties. But the space inside is filled with gluons, and with temporary pairs of quarks and antiquarks appearing and disappearing as part of the restless quantum field activity. The baryon is more like a churning, confined region of energy and fields than a little box with 3 permanent stones inside. This matters because it changes the answer to what a baryon is made of. If someone asks what a house is made of, we might say bricks, wood, glass, pipes, wires, and a few mysterious screws left over after assembly. But if someone asks what a proton is made of, saying 3 quarks is only the beginning. The proton is made of quarks, yes. It is also made of gluon fields. It is made of energy stored in those fields. It is made of motion. It is made of quantum fluctuations. It is made of the binding behavior of the strong force. The proton has mass not mainly because the individual quarks are heavy, but because the energy and dynamics of the strong force contribute so much. This is one of the most surprising truths in physics. Much of the mass of ordinary matter does not come from little solid bits having mass in the simple everyday sense. It comes from energy trapped and organised inside baryons. That is worth letting settle for a moment. The weight of your body, the weight of a mountain, the weight of the oceans, the weight of Earth itself comes largely from protons and neutrons. And the mass of those protons and neutrons comes largely from the restless energy of the strong force, from quarks and gluons moving and interacting inside a space so small that the word small begins to lose its usefulness. Matter feels solid and calm because at our scale, these inner storms average out into stable objects. A table does not tremble visibly because its protons are full of quantum activity. A cup of tea does not glow with the drama inside its atomic nuclei. Everything appears ordinary because the deep rules are reliable. This is one of the great comforts of physics, though perhaps a slightly odd comfort. The world is stable not because it is simple, but because its complexity is organised. A proton is not a quiet pebble. It is a bound state, a persistent pattern, a remarkably durable arrangement of quarks and gluons. It can last for longer than the age of the universe as far as experiments can tell, and yet inside it nothing is still. The proton is both steady and restless. It is a little like a city seen from far above at night. From a distance it looks like a single glowing shape. Up close it is roads, rooms, people, signals, engines, footsteps, conversations, kitchens, wires, and someone somewhere realizing they forgot to buy milk. The whole thing has one name, but inside that name is activity. The baryon is one of nature's ways of making a stable object from unstable ingredients. Quarks, as far as we know, are fundamental particles, but they are never found alone in ordinary conditions. This is another strange feature of the strong force. If you try to pull a quark out of a proton, the energy needed does not simply free it like pulling a pea from a pod. Instead, the energy can create new particles, and quarks remain confined inside composite particles. Nature seems to refuse to hand us an isolated quark. It is rather like trying to pull one end of a piece of elastic so far that instead of getting one end by itself, you suddenly have two pieces of elastic. This property is called confinement, and it is one of the central reasons baryons are so interesting. So when we ask what a baryon is really made of, we're also asking what kind of thing matter is at its foundation. Is it made of tiny objects? Yes, in one sense. Quarks are part of the answer. But is it made of empty space filled with fields? Also yes. Is it made of energy? Very much so. Is it made of relationships between particles, rules that determine what can separate and what must remain bound? Yes, again. Physics does not always reward us with one simple picture. Sometimes it gives us several pictures, each useful in its proper place, each incomplete if treated as the whole story. This can feel unsettling at first. We like building blocks. We like the idea that if we keep dividing matter, we will eventually find the smallest bricks from which everything is stacked. But baryons teach a subtler lesson. At very small scales, matter is not just a pile of smaller matter. It is structure. It is interaction. It is energy behaving according to rules. The familiar solidity of the world is what happens when those rules produce stable patterns. You're not made from inert microscopic grains in the way a beach is made from sand. You're made from atoms, whose nuclei are made from baryons, whose interiors are governed by quarks and gluons in constant quantum motion. And yet, this does not make the world less real. Quite the opposite. It makes ordinary things more impressive. A spoon is still a spoon. A stone is still a stone. Your hand is still your hand. But inside that hand are particles that have survived since the early universe, assembled into atoms, passed through stars, dust, planets, oceans, plants, animals, meals, memories, and now this quiet moment. The baryons in you are ancient, not in a mystical sense, but in a physical one. Many of the protons in your body have likely existed for billions of years, through astonishing changes in arrangement, becoming part of different materials, different organisms, different landscapes, but remaining themselves with almost absurd patience. There is something deeply grounding about that. Not poetic exactly, but practical in a grand way. The matter in you has a history. It has structure. It has rules holding it together. And tonight, as we begin looking into baryons, we're not stepping away from ordinary reality. We're stepping into the machinery that lets ordinary reality exist at all. We're asking why the centers of atoms are stable, why protons do not simply dissolve, why neutrons behave as they do, and why the strong force hidden from daily experience quietly supports almost every object we touch. The first thing to carry with us is that a baryon is not merely a tiny lump. It is a composite particle, a bound system of quarks held by the strong interaction. The second thing is that the simple phrase made of 3 quarks is helpful, but incomplete. The 3 quarks are important, but the full baryon includes the energetic field activity that binds and fills it. The third thing is that most of what we call mass in everyday matter is not sitting in the quarks as little stored weights. It arises from the energy of their motion and their binding. That is not a decorative detail. It is one of the deepest facts about the physical world. From here, the story naturally moves inward. We have stood outside the atom, then looked toward the nucleus, then noticed the proton and neutron, then opened the idea of the baryon just enough to glimpse the activity inside. Now we can begin to slow down and examine the heavy little hearts of matter more carefully. Because before we can understand the crowded interior of a baryon, it helps to understand why protons and neutrons matter so much in the first place, why they became the anchors of atoms, and why the universe chose these tiny heavy particles as the quiet foundation for stars, planets, and sleeping listeners with questions in the dark. To understand a baryon, it helps to begin with the most familiar baryons of all, even though they're hidden so well that we spend most of our lives never thinking about them. The proton and the neutron are not rare visitors from some remote corner of particle physics. They are the heavy little hearts of ordinary matter. They sit inside atomic nuclei, quietly giving atoms their mass, their identity, and much of their stubbornness. If electrons are the light, restless outer parts of the atom, shaping chemistry and deciding how atoms hold hands with one another, then protons and neutrons are the dense central gathering. They are the compact inner crowd that makes an atom more than a loose cloud of electric charge. Without them, the physical world would not simply be different. It would lose the kind of structure that lets rocks be rocks, oceans be oceans, and sleepy listeners rest their heads on pillows that do not drift away into radiation. The word heavy needs a little care here, because at the scale of everyday life a proton is not heavy at all. One proton is so tiny in mass that no kitchen scale, no matter how judgmental, could ever notice it alone. You could place a single proton on the most sensitive ordinary balance and it would not so much as twitch. But compared with an electron, a proton is enormous. A neutron is enormous too. They are both roughly similar in mass, and each is much heavier than the electron that moves around the atom. That is why nearly all the mass of ordinary atoms comes from the nucleus. The atom may extend outward through its electron cloud, but most of its weight is concentrated in the small central place where protons and neutrons live. It is a little like finding that nearly the entire weight of a large theatre is stored in a walnut at centre stage, which would make for a rather alarming architectural inspection. This dense centre is called the atomic nucleus. It is not large in the human sense, or even in the microscopic sense. It is far smaller than the atom as a whole. The atom is mostly space in terms of size, though not empty in the simple household meaning of the word. Quantum fields and electron behaviour fill that region in their own way. Still, compared with the wide reach of the atom, the nucleus is tiny. And yet it holds almost everything that makes the atom heavy. That fact alone should make the nucleus feel slightly suspicious. Nature has packed a great deal into a very small place, and whenever nature does that, physicists tend to appear with notebooks, machines, and the expression of someone who has just smelled toast burning in another room. Inside the nucleus, protons determine the element. This is one of the clearest rules in all of atomic physics. If an atom has one proton, it is hydrogen. If it has 2, it is helium. If it has 6, it is carbon. If it has 8, it is oxygen. The number of protons gives the atom its chemical identity. Add or remove a proton, and you have not merely adjusted the atom, you have changed it into a different element. This is why protons are not just heavy residents of the nucleus, they are identity markers. They are the reason one atom belongs to one element rather than another. The electron cloud may decide how atoms react and combine, but the number of protons tells the electrons what kind of atom they are dealing with in the first place. Neutrons are quieter in that respect, partly because they carry no overall electric charge. A neutron does not define the element the way a proton does. Instead, neutrons help shape the isotope. Atoms of the same element can have different numbers of neutrons, and these different versions are called isotopes. Some isotopes are stable, others are unstable and eventually decay. The neutron, though electrically neutral, is not unimportant. It helps hold the nucleus together. It changes the mass. It affects nuclear stability. It can decide whether an atom quietly endures for billions of years, or transforms after a brief stay in the world. The neutron is a little like the person in a group project who says less during the meeting but turns out to be the reason the whole thing actually works. The reason neutrons are needed becomes clearer when we think about electric charge. Protons are positively charged. Charges of the same kind repel each other, so if you pack several protons into a tiny nucleus, they should push apart. They should not want to sit together. In everyday terms, it is like trying to keep several people with umbrellas in a very small elevator, each insisting on opening theirs at once. There is pressure to spread out. For atomic nuclei to exist, some other force must overcome that electrical repulsion at very short distances. That force is the strong nuclear force. It acts between the particles in the nucleus and is powerful enough, over the tiny distances involved, to bind protons and neutrons into a stable central core. This is where baryons become central to matter. Protons and neutrons are not simply placed in the nucleus like peas in a bowl. They interact through the strong force. More precisely, the strong force has one form inside baryons, where it binds quarks, and a related leftover form between protons and neutrons inside nuclei. The details become subtle very quickly, but the practical result is easier to grasp. The nucleus holds together because strong interactions create binding. Without that binding, positively charged protons would repel each other too strongly, and the larger atomic nuclei needed for chemistry and life would not exist. Hydrogen might still be possible, because it needs only one proton in its nucleus, but the rich table of elements would disappear. No carbon for organic chemistry, no oxygen for water, no iron in blood, no calcium in bones, no gold wedding rings, which would be a shame for romance and for jewellers. The proton itself is stable as far as experiments have been able to show. This stability is one of the quiet miracles of ordinary matter. If protons decayed quickly, atoms would not last. Matter would be temporary in a much more dramatic way. You would not be able to build planets from particles that kept politely leaving existence after a few minutes. The world relies on the proton being extremely long-lived. The neutron is different. A neutron by itself, outside a nucleus, is unstable. Left alone, it will eventually decay into other particles. But inside many nuclei, neutrons can be stable because the nuclear environment changes what is energetically allowed. In other words, a free neutron is not quite comfortable by itself, but in the right nuclear company it can settle down. This is perhaps the most relatable particle behavior in physics. The stability of protons and the conditional stability of neutrons are not just technical details, they explain why matter has the shape it has. The universe after the Big Bang was once hot, dense, and full of particles. As it expanded and cooled, protons and neutrons formed and began participating in the first nuclear reactions. Simple nuclei appeared first, especially hydrogen and helium, along with small amounts of a few other light nuclei. Much later, stars became the great workshops where heavier elements were forged. Inside stars, nuclei fused together under extreme temperature and pressure. In the deaths of stars and in violent cosmic events, still heavier elements were made and scattered. The atoms in your body are part of that history. Their nuclei are not random collections. They are the results of cosmic processes that depended on protons and neutrons behaving in reliable ways. This gives baryons a very practical importance. When cosmologists speak of ordinary matter, they often mean baryonic matter. That is the matter made mostly of protons and neutrons, along with electrons. It includes stars, planets, gas clouds, dust, people, trees, tea, and the biscuit you may or may not have planned to eat but somehow did. Baryonic matter is the familiar stuff, the matter that shines, absorbs light, forms atoms, and gathers into the visible structures we can study with telescopes and instruments. It is not all the matter in the universe, because dark matter seems to be something else, but baryonic matter is the matter that makes the world directly available to our senses. The phrase ordinary matter can make baryon sound dull, but that would be unfair. Ordinary here does not mean simple, it only means familiar. A proton is ordinary in the same way the ocean is ordinary if you live near the coast. It may be common, but it is hardly plain once you study it. Every proton contains internal structure. Every neutron does too. Each one is a composite particle, a bound state of quarks and gluons with energy constantly moving through it. Yet from the outside, under many conditions, a proton behaves as a single particle with a definite charge, mass, and spin. This is one of the great balancing acts in physics. Something can be internally busy and externally stable. It can have a complicated inner life while presenting the world with a simple public face. Many people manage something similar at family gatherings. Because protons and neutrons are baryons, they also belong to a larger particle family. There are other baryons besides the proton and neutron. Some are heavier and unstable, some contain different kinds of quarks. They appear in high-energy experiments and extreme cosmic environments, but they do not make up the stable matter around us in the same way. The proton and neutron are special because they are the baryons that nature uses for building the long-lasting nuclei of everyday atoms. They are not the only baryons, but they are the ones that matter most to chemistry, biology, geology, and the quiet arrangement of your room at this moment. The proton has positive charge, and that positive charge attracts electrons. This attraction is what lets atoms form. A lone proton can hold an electron and make hydrogen, the simplest atom. Add more protons and neutrons in the nucleus, and more electrons can be arranged around it. The number of protons sets the positive charge of the nucleus, and the electrons arrange themselves according to quantum rules around that charge. The outer electron structure then determines how atoms bond with other atoms. So while chemistry is often described through electrons, those electrons are responding to the nucleus, and the nucleus is built from baryons. The baryons do not usually take part directly in chemical reactions, but they set the stage. They are like the foundation of a house. You may spend more time admiring the curtains and arguing about the sofa, but the foundation is quietly deciding whether the house remains a house. Neutrons add another layer to that foundation. They increase nuclear mass without adding positive charge. They help reduce the strain between protons in many nuclei, and they influence which combinations of protons and neutrons are stable. Light elements often have similar numbers of protons and neutrons. Heavier elements usually need more neutrons than protons to remain stable, because the growing electrical repulsion among protons becomes harder to manage. If a nucleus has too many or too few neutrons, it may become unstable and undergo radioactive decay. This is not a failure of nature, it is nature rearranging toward more stable possibilities. The nucleus is not merely a pile of particles, it is a system with rules, balances, and thresholds. Radioactivity is one way we see that nuclei are active systems, not dead lumps. Some nuclei emit particles or radiation as they change into other nuclei. These processes are essential in geology, medicine, archaeology, energy production, and astrophysics. They also remind us that the heavy little hearts of matter can change, though many do so slowly. Some isotopes decay in fractions of a second. Others endure for millions or billions of years, and some nuclei are stable for all practical purposes. The difference depends on nuclear structure, on the balance of protons and neutrons, and on the interactions that govern them. Baryons are not just ingredients, they are players in a constant negotiation over stability. At this point, it is useful to pause and separate two levels of explanation. At the nuclear level, protons and neutrons act as particles bound together inside nuclei. This is the level where nuclear physics often works. It studies how nuclei are built, how they decay, how they fuse, how they split, and how they behave in stars and reactors. At the deeper level, each proton and neutron is itself made of quarks and gluons. This is the level of particle physics and the strong interaction in its more fundamental form. Both levels are true. They are like two maps of the same countryside. One shows roads, towns, and rivers. The other shows soil chemistry and bedrock. Which one you use depends on the question you're asking. If you want to drive to the bakery, the geological map is not especially helpful, unless the bakery is underground and unusually serious about sedimentary layers. For many purposes, treating protons and neutrons as individual particles works beautifully. Nuclear models can explain an enormous range of phenomena without constantly tracking every quark and gluon inside every baryon. This is because nature often allows useful simplification. A proton inside a nucleus has inner structure, but the nucleus may still be modelled as if it contains protons and neutrons as whole units interacting with one another. That does not mean the deeper structure is irrelevant. It means the deeper structure can sometimes be packaged into effective behaviour. Physics does this often. It does not always need the deepest possible description for every problem. If you are calculating the flight of a thrown ball, you do not need to describe every atom in the ball. If you're making soup, You do not need quantum field theory, although it might make the recipe unnecessarily dramatic. Still, when the question is what a baryon is really made of, we cannot remain only at the nuclear level. We have to remember that protons and neutrons are not fundamental. Their heaviness, their charge, their spin, their magnetic behavior, and their ability to participate in nuclear binding all arise from their internal quark and gluon structure. But before going inside them, we need to appreciate what they do as whole particles. They create the nuclei that define atoms. They carry most of the mass. They allow complex elements to exist. They make stars possible by providing the material that fusion can act upon. They create the baryonic matter from which visible cosmic structures are built. In a very real sense, baryons are how the universe turns high-energy particle physics into furniture. This is why the heavy centre of the atom is so important. It is not just a storage place for mass. It is the anchor that gives atoms their identity and persistence. Electrons are light and mobile. They can be shared, transferred, excited, rearranged. Chemistry is full of electron movement, but the nucleus changes only under more extreme conditions. That difference gives matter a layered stability. Chemical processes can be lively and flexible while nuclear identities remain mostly steady. You can burn wood, digest food, freeze water, melt metal, or bake bread, and the nuclei usually remain the same elements. The atoms rearrange into new molecules, but the protons and neutrons inside their nuclei mostly continue on as before. This is rather fortunate because if making toast regularly changed the nuclei in your kitchen, breakfast would require licensing. There are exceptions, of course. Nuclear reactions do change nuclei. Fusion in stars combines light nuclei into heavier ones. Fission splits heavy nuclei into smaller pieces. Radioactive decay transforms unstable nuclei over time. Particle collisions can create new baryons, break apart nuclei, or reveal internal structures. But in everyday life, nuclear matter is mostly steady. That steadiness is part of why the world feels reliable. The objects around you are built from atoms whose nuclei are not casually changing during normal use. A book remains made of the elements it was made of. A glass of water remains water unless chemical or physical changes occur. The baryons in the nuclei quietly keep their posts. It is easy to overlook how much this reliability depends on the strengths and balances of fundamental forces. If the strong force were much weaker, atomic nuclei beyond hydrogen might not hold together. If it were much stronger in different ways, nuclear processes in stars could change dramatically. If the electromagnetic repulsion among protons were different, the stability of elements would shift. The universe that allows ordinary matter is not a random heap. It is a system in which forces and particles have properties that permit structure. Baryons sit at the centre of that structure, not because they are large, but because they are stable enough, massive enough, and interactive enough to build upon. Their mass deserves special attention. When we say the nucleus contains most of the atom's mass, it is tempting to imagine that protons and neutrons are heavy, because their internal quarks are heavy. But the quarks inside ordinary protons and neutrons are relatively light compared with the baryon as a whole. Most of the mass comes from the energy of the strong interaction, from the motion and confinement of quarks and gluons. This turns the everyday idea of weight inside out. The mass you feel when you lift an object is, to a large extent, the mass of bound energy inside baryons. The object resists acceleration because of energy organized into stable particles. Your hand pressing against a table is interacting with matter whose solidity comes from electromagnetic effects among atoms, but whose mass is rooted mainly in the energetic interior of protons and neutrons. This is not a metaphor. It is a physical statement about where ordinary mass comes from. That can make matter seem less like stuff, and more like activity that has learned to stay put. But stay put is not quite right either, because everything inside remains active. A proton is stable, yet its interior is not frozen. Quarks and gluons are constantly interacting. The neutron is similar, though its overall electric charge is neutral because its internal charge is balance. From the outside, the neutron seems electrically quiet. Inside, it contains charged quarks whose combined effect cancels overall. This is a good reminder that neutrality does not always mean absence. Sometimes it means balance. A neutron is not empty of charge structure. It is arranged so that the total comes out neutral, a little like a household budget that looks calm only because several dramatic expenses and deposits have cancelled each other by the end of the month. The proton and neutron are close relatives. They are similar in mass, similar in size, and built from the same types of light quarks in different arrangements. This closeness is why they can form nuclei together so effectively. Yet the difference between them is crucial. The proton's positive charge attracts electrons and defines elements. The neutron's neutrality helps stabilize nuclei without adding more electric repulsion. Their partnership is one of the basic arrangements that makes complexity possible. Too many protons without enough neutrons, and nuclei become unstable. Too many neutrons and other instabilities appear. The stable elements occupy a kind of narrow valley in the landscape of nuclear possibilities. Ordinary matter lives there, in the region where baryons have found workable arrangements. In laboratories, physicists can explore what happens outside that valley. They create unstable nuclei with unusual numbers of neutrons or protons. They study short-lived baryons that appear only in high-energy collisions. They observe how nuclear matter behaves under extreme conditions, including conditions that may exist inside neutron stars. A neutron star is what can remain after a massive star collapses, leaving matter compressed to astonishing density. In such an object, baryons are packed so closely that ordinary nuclear ideas are pushed to their limits. Neutrons dominate, and the matter may contain exotic particles or phases that are still actively studied. So the humble neutron in an atom and the neutron-rich matter inside a collapsed star are part of one long story. Baryons are not only the hearts of atoms. Under extreme conditions, they become the material of some of the densest objects in the universe. And yet, the same family of particles is present in you right now. That is perhaps the most useful way to stay grounded while thinking about baryons. They are not just things in accelerators or neutron stars. They are inside every atom of your body except for the simplest cases where a nucleus may be just a proton. They are in the floor, the walls, the air, the lamp, the glass, the trees outside if there are trees nearby, and the clouds whether or not you can see them. Baryons are the quiet majority of visible matter's mass. They do not glow with importance. They do not announce themselves. They simply hold the centre. When we look at the heavy little hearts of matter, then, we are looking at a bridge between scales. On one side is the world we touch, full of materials and textures. On the other side is the hidden world of quarks, gluons, fields, and confinement. Protons and neutrons sit between them. They are small enough to belong to particle physics, but large and stable enough to become the building blocks of nuclei. They are not fundamental, yet they are foundational. That distinction matters. Something does not need to be the smallest possible thing to be one of the most important things. A brick is not fundamental in the deeper sense, but houses still need bricks or something like them. A word is made of letters, but a story is not explained by letters alone. A proton is made of quarks and gluons, but the physical world is not explained by naming the quarks and walking away. So before we open the proton more carefully, it is worth holding on to this picture. A baryon is a composite particle, but in ordinary matter it often acts as a dependable unit. Protons and neutrons gather into nuclei. Nuclei anchor atoms. Atoms form molecules. Molecules form materials. Materials form planets, oceans, cells, and the quiet furniture of daily life. This chain of structure depends on the baryon's unusual combination of inner complexity and outer reliability. It is small, but heavy. Busy, but stable. Composite, but able to behave as one. Hidden, but responsible for much of what we call matter. And once that is clear, the next question becomes harder to avoid. If the proton and neutron are not simple objects, what are the pieces inside them doing? The usual answer begins with 3 quarks. But that phrase can be misleading if it makes the interior sound tidy. The inside of a baryon is not a neat little arrangement of 3 pellets. It is a crowded, energetic, strongly bound system, where quarks are constantly moving, gluons are constantly carrying the interaction, and the boundary between particle and field becomes much less like ordinary common sense. So we move closer now, not to make the picture simpler, but to make it more honest, into the strange little room where 3 quarks somehow become 1 baryon. The proton and neutron look simple from far away, in the same way a city looks simple from an airplane at night. You see one glowing shape, one patch of brightness, one thing with a name. London, Paris, Tokyo, a proton. From a distance, each seems almost tidy. But the closer you go, the more the single shape becomes roads, rooms, signals, motion, noise, and countless little interactions happening all at once. A baryon is like that. From outside, it behaves as one particle. It has one mass, one overall electric charge, one identity in the particle catalogue. But when physicists look inside, they find not a quiet bead, but a crowded little region where quarks and gluons are never still. The simplest way to begin is with the familiar phrase that a baryon is made of 3 quarks. A proton is often described as 2 up quarks and 1 down quark. A neutron is often described as 1 up quark and 2 down quarks. This is not wrong. It is the first useful answer, and it is one of the most important facts in modern particle physics. But it is also a little too tidy. It can make the proton sound like a tiny bag with 3 marbles in it, perhaps 1 marble sitting in each corner, politely waiting for a scientist to count them. The real proton is much livelier than that. The 3 quarks are important, but they are not sitting still, not sharply located like beads in a box, and not alone in an empty space. They are part of a dense quantum system held together by the strong interaction, surrounded and connected by gluons, with temporary quark and antiquark pairs flickering through the interior as part of the field activity. So we should treat the phrase 3 quarks as a doorway, not as the whole room. It tells us how the baryon is classified, but it does not tell us everything that is happening inside. Those 3 quarks are called valance quarks. That name is borrowed from the idea of valance in chemistry, where certain electrons help determine how atoms bond. In a baryon, the valance quarks help determine the particle's identity. They set the broad pattern. They are the reason a proton is a proton and a neutron is a neutron. If you change the mixture of valence quarks, you change the baryon. But just as a city is not fully described by saying it has 3 main roads, a baryon is not fully described by naming 3 valence quarks. Let us start with the quarks themselves. Quarks are fundamental particles, as far as current experiments can tell. That means physicists have not found smaller pieces inside them. They do not appear to be little composite objects made of something else, at least not at the scales we have been able to probe. Quarks come in several types, often called flavors. The names are a little whimsical: up, down, strange, charm, bottom, and top. These names do not mean what they sound like in daily language. An up quark is not floating upward. A strange quark is not necessarily behaving suspiciously near the biscuits. These names are labels for different kinds of quarks with different properties such as mass and charge. The up and down quarks are the lightest and most important for ordinary matter because protons and neutrons are built from them. The electric charges of quarks are unusual when compared with the charges we meet in ordinary particles. An electron has 1 unit of negative charge. A proton has 1 unit of positive charge. Quarks have fractional charges, smaller pieces of charge that combine to make the whole charge of a baryon. 2 up quarks and 1 down quark combine to give the proton its positive charge. 1 up quark and 2 down quarks combine to give the neutron no overall electric charge. This is one of those facts that sounds almost like accounting. Add the charges in the right combination, and the total becomes proton or neutron. But again, the accounting is only the outer result. Inside, the charges belong to particles in motion, interacting through the strong force surrounded by fields. the existence of quarks was not immediately accepted when first proposed. At first, they were a way to organise a growing zoo of particles discovered in cosmic rays and particle accelerators. Physicists had found many heavy particles, more than anyone expected if nature was supposed to be simple. It was rather as if someone opened a cupboard looking for 1 or 2 plates and found an entire restaurant stacked inside. The Quark model brought order to that confusion. It suggested that many of those particles were not fundamental after all, but combinations of smaller ingredients. Baryons were made from 3 quarks. Another family of particles called mesons were made from a quark and an antiquark. With this idea, the particle zoo began to look less like chaos and more like a pattern. At first, quarks may have seemed like mathematical conveniences, useful for organising particles but perhaps not real in the same sense as electrons or protons. Then experiments began to show that protons had internal structure. High-energy particles were scattered from protons, and the results suggested that hard point-like constituents were inside. These constituents matched the quark picture. The proton was not featureless. It had parts. But even here, nature avoided making things too easy. The quarks inside a proton could not be removed and placed in a jar for inspection. No one has ever isolated a single free quark under ordinary conditions. Quarks are confined. They appear only inside composite particles, locked into combinations that nature permits. This confinement is one of the defining mysteries of the strong interaction. With electric forces, if you separate 2 charged particles, the force generally becomes weaker as they move apart. With quarks, the strong interaction behaves differently. Try to pull quarks apart, and the field between them resists in a way that does not simply fade like an ordinary stretched spring. If enough energy is added, the system tends to create new quark combinations rather than release one quark alone. It is not like opening a box and removing a marble. It is more like trying to pull one end of a rubber band until, instead of getting a loose end, you create a new pair of ends. The quark remains part of a bound particle. Nature seems to insist that quarks travel in company. Now imagine those 3 valence quarks inside a baryon. It is tempting to ask where exactly each one is. Is one on the left, one on the right, one in the middle? Does the proton have a tiny internal map? Quantum mechanics does not allow such a simple picture. The quarks do not have sharply defined positions in the way coins on a table do. They are described by quantum states, spread out in probability, interacting constantly. Their motion is intense. They are confined within a tiny region, and confinement means they have energy. The uncertainty of their positions and momenta is part of the story. A baryon is not a static arrangement. It is a dynamic state, a pattern of activity that remains stable overall even though the details inside are ceaselessly changing. This is where the crowded room becomes useful as a mental image, as long as we do not take it too literally. Picture a room so small that the occupants cannot stand apart in any ordinary way. They are not calm guests at a polite dinner party. They are moving, exchanging signals, bumping through possibilities, and being held together by a force so strong that leaving the room alone is not an option. But even this picture is too ordinary, because the room itself is made of fields, and the signals are gluons, and the occupants do not behave like little people with elbows. Still, it helps us remember the main point. The inside of a baryon is full. The gluons are essential. They are the carriers of the strong force. In a simple first picture, quarks exchange gluons, and this exchange binds them together. But gluons are stranger than that. Unlike photons, which carry the electromagnetic force but do not carry electric charge themselves, gluons carry the kind of charge associated with the strong force. This charge is called colour charge. It has nothing to do with visible colour. Quarks are not actually red, green, or blue in the visual sense. Those words are just labels, chosen because the combinations have a useful analogy with colours combining to make neutrality. It is a naming scheme, not a paint sample. If someone could somehow see a quark, which is not how seeing works at that scale anyway, it would not look like a tiny red dot or a tiny blue dot. Color charge is the property that lets quarks feel the strong interaction. A baryon must be color neutral overall. The three quarks combine their color charges in such a way that the whole baryon has no exposed color charge. This is one reason three quarks can form a baryon. Their color charges can balance. But since gluons carry color charge too, they interact not only with quarks but with each other. That self-interaction makes the strong force very different from electromagnetism. It creates a complicated field environment inside the baryon, a dense web of interactions that cannot be reduced to three quarks pulling on each other with simple strings. This complicated activity is one reason the proton's mass is so surprising. If you add up the masses of the up and down valence quarks alone, you get only a small portion of the proton's mass. Most of the proton's mass comes from the energy of the gluon field, the motion of the quarks, and the dynamics of confinement. The baryon is heavy not because it contains three heavy stones, but because it contains a strongly bound energetic system. Its mass is the mass of activity, the mass of fields and motion, the mass of energy held in a stable pattern. This is not how matter seems at first glance. We tend to imagine weight as belonging to pieces of stuff. In the proton, much of the weight belongs to the energy that keeps the pieces from being free. That fact gives a slightly different feeling to the word made. In ordinary life, made of often means parts that can be separated and laid out. A sandwich is made of bread, filling, and the optimistic belief that it will not fall apart before lunch. A chair is made of wood or metal or plastic. A wall is made of bricks or plaster. If you take these things apart carefully, you can usually identify the ingredients. But a baryon cannot be taken apart into three isolated quarks and a tidy pile of gluons. The ingredients are bound in a way that changes what it means to be an ingredient. Quarks are real, but the baryon is not just a container. It is the entire strongly interacting system. The binding is not an accessory, it is part of the object. The temporary quark and antiquark pairs inside the baryon deepen this point. Quantum fields are not empty, even in regions that seem quiet. In the interior of a proton or neutron, energy and field interactions can produce short-lived pairs of quarks and antiquarks. These are sometimes called C-quarks, because they form a kind of shifting background around the valence quarks. The valence quarks determine the main identity, while the C-quarks and gluons contribute to the full behaviour of the baryon. The word C is helpful because it suggests motion and depth. A proton is not three boats floating on nothing. It is boats, waves, currents, weather, spray, and perhaps one gull that refuses to explain itself. This C is not optional. It affects measurable properties. When high-energy experiments probe the proton, they see that its momentum is shared among quarks, antiquarks, and gluons. The valence quarks carry part of it, but gluons and C-quarks carry a great deal too, especially at high energies. This means the proton seen by a fast-probing particle is not simply three objects. It is a swarm of constituents whose appearance depends on how you look. At lower energies, the proton behaves more like a single whole particle. At higher energies, its inner parton structure becomes visible. Parton is a general term used for the constituents seen in high-energy scattering, including quarks and gluons. The word sounds like it should be part of a small engine, but it belongs to the inner workings of matter. There is another subtle issue. When we say a proton contains two up quarks and one down quark, we are talking about the valence quark content. But because of the C, the proton can also contain temporary strange quarks, charm quarks, and their antiquarks in tiny contributions, depending on the energy scale and the process being studied. This does not mean the proton becomes a strange baryon in the ordinary classification. Its valence structure remains that of a proton, but it reminds us that the interior is not a closed little cupboard with only three labelled jars. The quantum fields allow temporary activity that contributes to the full, physical reality of the particle. This is one of the reasons particle physicists are careful with language. Simple statements are useful, but they have ranges where they apply. A proton is made of 3 quarks is a good introduction. A proton is a bound state of quarks and gluons with 3 valence quarks is more accurate. A proton is an excitation of quantum fields, with a complex internal structure governed by the strong interaction is deeper still, though not as friendly to say before bedtime. Each version is trying to describe the same thing at a different level. The trick is not to throw away the simple picture too quickly, but not to mistake it for the final picture either. The neutron follows the same logic. It has 1 up valence quark and 2 down valence quarks. That arrangement gives it no net electric charge, even though the quarks inside have charges. The neutron is neutral overall but internally structured. It has a magnetic moment, which tells us that charge and motion inside are doing something measurable. A featureless neutral particle would not behave in quite the same way. The neutron's inner quark structure matters. Its neutrality is a balanced result, not a blank absence. In some ways, the neutron is even more quietly mysterious than the proton. It sits in nuclei helping hold matter together, but when free it decays. It is electrically neutral, yet internally active. It is ordinary, yet not simple. As we move deeper, it becomes harder to picture quarks as tiny solid balls. In quantum field theory, particles are excitations of fields. A quark is not a speck of hard material in the old-fashioned sense. It is a quantum object with properties such as mass, charge, spin, flavor, and color charge. It can be localized in interactions, but it is not a miniature bead with a painted surface. The same is true of gluons. They are not little drops of glue flying back and forth. They are quanta of the strong field, carrying color charge and interacting with one another. The baryon is a stable excitation pattern of these fields. That may sound less concrete than marbles, but it is the language that best matches experiments. Still, our brains like images, and there is no harm in using them gently. Imagine a baryon as a tiny storm that keeps its shape. The air inside a storm moves constantly, but the storm can remain recognizable as one system. Or imagine a whirlpool in water. The water molecules are always changing position, but the whirlpool pattern persists. A baryon is not literally a storm or a whirlpool, but these images capture the difference between a static object and a stable process. A baryon is stable not because nothing changes inside it, but because the pattern of change is governed and bound. It is persistence through motion. This persistence is astonishing. Protons appear to be extraordinarily stable. If they decay at all, their lifetimes are far beyond ordinary cosmic history. That means the internal storm of a proton can endure for billions of years. The quarks and gluons inside remain in restless interaction, but the whole object continues as a proton. It can become part of a hydrogen atom in a star, then part of water on a planet, then part of a living cell, then part of the air, and through all that rearrangement, the proton itself remains. The proton is not fragile in the way its busy interior might suggest. It is more like a spinning top that never quite falls, except even that is too mechanical and too calm. The 3 valence quarks also give baryons their membership in a larger family. If the valence quarks include heavier flavors, the baryon changes. A baryon containing strange quarks is different from a proton or neutron. Baryons with charm or bottom quarks can be produced in particle accelerators, but they are unstable and decay quickly. The top quark is so short-lived that it does not form ordinary bound baryons in the same way before it decays. This family structure shows that the 3-quark idea is powerful. It organizes many particles, predicts relationships, and explains why certain combinations exist. But the stability of the proton and neutron is special, because up and down quarks are light and can form long-lasting baryons suitable for ordinary nuclei. There is a useful comparison with chemistry. Carbon atoms can bond in many arrangements, making diamond, graphite, sugars, proteins, plastics, and living tissues. The same basic element can participate in many structures. In particle physics, quarks combine according to the strong interaction to form different hadrons. Baryons are one class of hadrons, mesons are another. The rules are not chemical rules, and the scales are vastly smaller, but the principle of combinations producing variety is familiar. Nature often builds richness from a limited set of ingredients and rules. It is economical in a way that still manages to be extravagant. The room inside a baryon is crowded not because it has many permanent residents in the ordinary sense, but because fields in a confined region are active. A proton is not mostly empty space in the same way an atom is often described as mostly empty. Its interior is filled with strong fields and quantum activity. The energy density is enormous. The quarks move at high speeds. Gluons carry momentum. See quarks appear in the description. The whole object is tiny, but its inner life is intense. When we hold an object in our hand, we are holding matter whose mass is rooted in countless such interiors. The calm surface of the object hides a staggering amount of microscopic motion and binding. Now, why 3 quarks for baryons? The answer comes from the rules of the strong interaction and colour neutrality. Quarks carry colour charge, and only colour-neutral combinations are found as free particles. 3 quarks can combine into a colour-neutral baryon. A quark and an antiquark can combine into a colour-neutral meson. There are also more exotic combinations, such as particles made from 4 or 5 quarks in certain arrangements, and these have become an active area of research. But the ordinary baryons of everyday matter are 3 valence quark systems. The proton and neutron are the stable representatives that build nuclei. The rule is not arbitrary. It arises from the structure of the theory that describes the strong force. That theory is called quantum chromodynamics. The name sounds grand, and it is. It is the modern theory of quarks and gluons. Chromo refers to colour charge, again not visible colour, but the strong charge labels. Dynamics refers to how those charges and fields behave. Quantum chromodynamics is remarkably successful, but it is also difficult to work with in the energy range that matters for protons and neutrons. The strong force becomes strong enough that simple calculation methods often fail. Physicists use powerful numerical techniques, including simulations that place the theory on a space and time grid, to calculate baryon properties from the underlying quark and gluon rules. This is not the sort of arithmetic one does on the back of a napkin, unless the napkin is the size of a warehouse and connected to a supercomputer. These calculations have confirmed something profound. The properties of protons and neutrons can arise from the theory of quarks and gluons. Their masses, interactions, and many features are not arbitrary. They emerge from the strong force. This is one of the great achievements of modern physics, turning the messy inner life of baryons into a computable, testable description. It does not mean every detail is easy. Far from it. The proton continues to offer puzzles, including how its spin is built from the contributions of quarks, gluons, and their motion. Even one of the most common particles in the universe still has questions tucked inside it, like a familiar coat with strange receipts in the pocket. The spin of the proton is a good example of why 3 quarks is not enough as a final picture. Early expectations suggested that the spins of the quarks might simply add up to the spin of the proton. Experiments show the situation is more complicated. Quark spins contribute, but so do gluons and orbital motion inside the proton. The proton spin is a property of the whole internal system, not just a simple sum of 3 little arrows. Again, the baryon behaves as one particle from outside, but its one particle properties are collective results. The whole is not just the parts placed next to each other. It is the parts interacting under strict quantum rules. This is perhaps the central lesson of the crowded room. A baryon is made of quarks, but not in the way a necklace is made of beads. It is made of quarks in interaction, quarks in fields, quarks confined by gluons, quarks accompanied by temporary pairs, quarks whose behaviour cannot be separated from the strong force that binds them. The baryon is the room and the crowd and the rules of motion all at once. If you remove the strong force, you do not get the same baryon minus its glue. You get no baryon at all. The binding is part of the identity. At our everyday scale, none of this is visible. The proton in a hydrogen atom behaves as a compact positive charge. The neutron in a nucleus behaves as a neutral nuclear particle. Their internal structure is hidden unless we probe at high energies or ask very precise questions. This hiddenness is a gift. It lets chemistry work without requiring every molecule to keep track of gluon fields in detail. It lets biology operate with atoms and bonds rather than with the full machinery of the strong interaction. Nature builds levels. Each level has its own useful language. The level of cells, the level of molecules, the level of atoms, the level of nuclei, the level of quarks and gluons. None cancels the others. They stack, overlap, and support one another. So when someone asks what a baryon is really made of, the honest answer starts with 3 valence quarks, but then immediately becomes richer. It is made of 3 defining quarks, yes, but also of gluons carrying the strong force between them. It is made of C-quarks and antiquarks that appear through quantum field activity. It is made of motion and binding energy. It is made of color charge arranged so the whole particle is neutral under the strong interaction. It is made of a stable pattern in fields, a small but persistent structure that can act as a single particle while containing extraordinary internal complexity. The proton and neutron are therefore not simple centers of atoms. They are more like sealed engines of the strong force, running without fuel in the ordinary sense, powered by the rules of quantum fields themselves. Their interiors are impossible to picture perfectly, but not impossible to understand in stages. First, we learn that they are baryons. Then we learn that baryons contain 3 valence quarks. Then we learn that those quarks are never alone. Then we learn that gluons fill the story so completely that most of the mass comes from the field energy rather than the quark masses. Each step makes the picture less like a child's model and more like the real thing, and this prepares us for the next layer of the question. If 3 quarks are confined in such a small space, what actually holds them there? What is the strong force doing that ordinary forces do not do? Why do gluons make the inside of a baryon so crowded? And why does pulling on a quark not simply free it? The answer leads into the gluon sea, that restless field of strong interaction that turns 3 quarks into one enduring particle, and turns the deep interior of matter into something far more active than the solid world above it suggests. The moment we stop imagining quarks as little marbles and begin thinking of them as participants in a powerful field, the baryon starts to look less like a container and more like a process. The proton is not a quiet shell with 3 objects tucked neatly inside. The neutron is not a small neutral box with different contents. Each is a bound system, and the binding is not something added afterward, like string around a parcel. The binding is part of what the baryon is. If the quarks are the named characters, then the gluons are the conversation, the pressure, the movement, the rules of the room, and quite a lot of the furniture as well. Without the gluon field, the quarks would not form a proton or a neutron. They would not be gathered into the heavy little centers of atoms. They would not give matter its familiar weight and persistence. The gluon sea is not background decoration. It is the living mechanism that makes a baryon a baryon. The word gluon sounds almost too simple for the job it does. It suggests a tiny particle of glue, perhaps a little sticky bead flying between quarks and holding them together with microscopic paste. That picture is charming, and it is not a terrible place to begin, but it becomes misleading very quickly. Gluons are not glue in the ordinary sense. They are the carrier particles of the strong interaction, the force associated with quarks. They are the way the strong field communicates. In the same broad way that photons are connected with the electromagnetic force, gluons are connected with the strong force. But the comparison only goes so far because gluons have a special complication. Photons do not carry electric charge, so they do not directly pull on each other through electromagnetism. Gluons carry the charge of the strong force, which is called color charge. That means gluons can interact with other gluons. The messengers talk not only to the quarks, but also to one another. This one fact changes everything. In a simple picture of electromagnetism, charged particles exchange photons, and the force between them can often be handled with clean mathematical tools. With the strong interaction, The force carriers are themselves charged under the very force they carry. The result is a self-interacting field. It is as if every messenger in a crowded office not only delivers notes, but also writes notes to every other messenger while running down the hallway. Very soon, the hallway is no longer a passive space. It becomes part of the activity. Inside a baryon, the gluon field is not a set of occasional signals passing through emptiness. It is a dense, active, changing sea of field energy. Color charge deserves a careful pause, because the name can easily give the wrong impression. Quarks do not have visible colors. A quark is not red or blue like a button, a berry or a suspiciously bright sweet in a packet. Color is a label physicists use for the kind of charge involved in the strong interaction. It comes in types that can combine in certain balanced ways, and the words chosen for those types borrow from ordinary color language because the analogy is useful. A baryon contains 3 valence quarks, whose color charges combine so that the whole baryon is color neutral. That neutrality is important. Nature does not allow isolated objects with exposed color charge to appear freely at large distances. The particles we observe as independent objects, such as protons and neutrons, are color neutral overall. This is a little like requiring every group leaving a building to have a complete set of passes, so that no one with an unfinished badge arrangement ever gets out alone. That image is not exact, but it captures the strictness of the rule. Quarks carry color charge, but free quarks are not seen. They are confined inside color-neutral combinations. Baryons are one such combination. Mesons made from a quark and an antiquark are another. There are also more exotic combinations that can be color-neutral in more complicated ways. But for ordinary matter, the proton and neutron are the reliable examples, and their existence depends on the strong field arranging color charge into a hidden balanced whole. Inside a baryon, the quarks are held so tightly that it is natural to ask why they do not simply settle into place, like stones at the bottom of a pond. The reason is that the quantum world does not allow this kind of stillness. Quarks are confined to a tiny region, and confinement means motion. Their positions and momenta cannot both be fixed with perfect precision. The more tightly a particle is confined, the more restless its motion becomes in the quantum description. The quarks inside a baryon are not sitting. They are moving intensely, exchanging gluons, interacting with the field, and contributing to the overall energy of the system. The baryon remains stable, but its stability is not the stability of a statue. It is the stability of a whirlpool, a flame, or a busy railway station that somehow keeps the same timetable most of the time, which is more than can be said for some actual railway stations. The strong force has another unusual property. At very short distances, quarks can behave almost as though they are relatively free inside the baryon. This does not mean they are free to leave. It means that when they are very close together, the interaction has a kind of looseness that surprised physicists when it was first understood. But as quarks are pulled farther apart, the strong field does not simply fade away in the familiar way of many everyday forces. Instead, the energy in the field grows. The connection between quarks becomes more resistant, not less. This is part of the reason confinement happens. Pulling a quark away does not produce a lonely quark drifting off into space. If enough energy is put into the field, new quark and antiquark pairs can be created, and the result is new particles, not isolated quarks. A simple household comparison would be stretching a piece of elastic, except that even this comparison breaks down. If you stretch ordinary elastic too far, it snaps, and you get 2 pieces. In the strong interaction, adding energy can lead to the creation of new particles. Instead of freeing one quark, nature reorganizes the energy into new color neutral combinations. This is one reason particle accelerator collisions produce sprays of particles called jets when quarks and gluons are involved. The quark or gluon that is knocked hard in a collision cannot appear alone. It becomes the starting point for a cascade of new particles as the strong field turns energy into color-neutral matter. It is as if the universe has a strict rule against letting quarks attend parties unaccompanied. This behaviour is called confinement, and it is one of the most important facts about baryons. A proton is not held together by a force that can be overcome in the usual sense to reveal 3 free quarks. You can break nuclei apart, you can knock protons out of atoms, you can ionize atoms by removing electrons. But pulling a proton apart into 3 separate quarks is not like pulling apart a machine. The energy you add changes the system. It creates more strongly interacting particles. The quarks remain hidden inside hadrons, the general family of particles made from quarks. That hiding is not due to poor technology. It is built into the behaviour of the strong interaction as we understand it. The word C helps because it reminds us that the inside of a baryon is not just 3 valence quarks connected by a few simple lines. The gluon field is full of energy. It fluctuates. It produces temporary quark and antiquark pairs. It carries momentum. In high-energy experiments, when a proton is probed very deeply, it appears as a collection of many constituents. The 3 valence quarks are present, but there are also gluons and C quarks. Depending on how the proton is observed, the gluons can carry a very large share of its momentum. The picture changes with the energy of the probe. A soft probe may see the proton as one particle. A sharper probe sees internal structure. A very energetic probe sees a crowded swarm of quarks, antiquarks, and gluons. The proton is not changing its identity in some dramatic theatrical way. It is that different questions reveal different aspects of the same object. This can feel odd, because we are used to objects having one fixed description. A cup is a cup whether you look at it from across the room or hold it in your hand. Of course, if you look with a microscope, you see ceramic grains or glass structure. Look deeper, and you see atoms. Look deeper still, and you find nuclei and electrons. At each scale, the cup has a different useful description. The proton is similar, except that the scale changes are much more extreme, and the rules become deeply quantum. From far away it is a single positive particle. Up close, it is a baryon with valence quarks. Deeper still, it is a sea of interacting fields. None of those descriptions is simply false. Each belongs to a level of detail. The gluon sea is also the key to understanding why a baryon has so much mass. This may be the most surprising part of the story. The up and down quarks inside protons and neutrons are not heavy enough by themselves to account for the mass of the proton or neutron. If you tried to explain the proton's mass by adding the masses of its 3 valence quarks, you would come up very short. Most of the mass comes from the energy of the quarks, and gluons moving and interacting inside the confined region. The strong field stores energy. The quarks have kinetic energy. The gluons carry energy. The whole bound system has a mass because energy and mass are deeply related in physics, though we do not need to write the famous equation to understand the point in words. The weight of ordinary matter comes largely from the energy of the strong interaction trapped inside baryons. This turns the everyday idea of matter inside out. We tend to think that mass belongs to little pieces of stuff. A brick is heavy because it contains stuff. A stone is heavy because its material is dense. But when you trace the mass of that brick or stone down into the nuclei of its atoms, and then into the protons and neutrons in those nuclei, you find that much of the mass is not the mass of small solid pieces. It is energy in a bound quantum system. The mass of the visible world is, to a large extent, the mass of the gluon sea and the motion it sustains. A mountain feels heavy because countless baryons contain fields in intense, confined activity. This is not what it looks like from the outside, but physics has never promised that the universe would arrange itself to match our first impression. There is a gentle irony here. The strongest force in ordinary matter is the one we never directly feel as a separate everyday sensation. We feel electromagnetism constantly. It is involved when our hands touch a table, when light reaches our eyes, when chemical bonds form, when nerves send signals. Gravity is weak compared with other forces, but it shapes our daily experience because Earth is large and persistent about pulling us downward. The strong force, however, is hidden inside nuclei and inside baryons. It acts over extremely short distances. We do not feel it directly when we pick up a spoon. Yet without it, the spoon would not have stable nuclei in the first place. The strong force is like a quiet engineer deep under the floor, never seen in the dining room, but responsible for keeping the building from becoming an inconvenient cloud. Inside the baryon, gluons create a kind of pressure and binding that cannot be separated from the identity of the particle. Some models describe quarks as if they're trapped inside a bag, with the strong field and quantum effects creating a boundary that confines them. Other descriptions use more direct calculations from the theory of the strong interaction. These are different tools and each has its uses. The deeper theory is called quantum chromodynamics, and it describes quarks and gluons through color charge. The theory is elegant in its foundations, but difficult in practice at the energy scales of protons and neutrons because the interaction becomes strong. Simple approximation methods that work well in some parts of physics often fail here. To calculate baryon properties accurately, physicists may use enormous computer simulations that represent space and time as a grid and let the fields evolve according to the rules. This is slow, demanding work, but it has shown that the masses and many properties of baryons can emerge from quarks and gluons. That word emerge matters. A proton is not made by taking 3 quarks with fixed masses, adding a few gluons and getting a result like assembling a toy. Its properties emerge from the interacting system. The mass, size, magnetic behavior, and internal momentum distribution are collective outcomes. The 3 valence quarks help define what kind of baryon it is, but the gluon C gives much of the substance to the answer. If you remove the C from your mental picture, the baryon becomes too light, too empty, too simple. It is like describing a thunderstorm by mentioning only 3 raindrops. The self-interaction of gluons also explains why the strong field can form flux structures between quarks. In some simplified pictures, the color field between quarks can be imagined as concentrated into tubes of field energy. Again, this is only a picture, but it helps explain why pulling quarks apart costs increasing energy. The field does not spread out loosely the way an electric field can. It can behave more like a stretched connection, storing more energy as separation grows. At some point, it becomes energetically favourable for the system to create a new quark and antiquark pair rather than keep stretching. Then new colour neutral particles form. This is one of the ways the gluon field turns energy into matter in high-energy events. It is important not to imagine gluons as little permanent strings tied between fixed quarks. The interior is quantum and dynamic. Gluons can be emitted and absorbed. They can split into other gluons. They can produce quark and antiquark pairs. The number of gluons inside a proton is not fixed the way the number of legs on a chair is fixed. It depends on how the proton is being examined and at what energy scale. The valence quark number gives a stable classification, but the full internal population is flexible and scale-dependent. This is why physicists speak of distributions rather than simple inventories when describing the proton's interior. They ask how momentum is shared among partons, how spin is distributed, how quarks and gluons contribute at different scales. It is less like counting marbles, and more like describing the weather inside a sealed universe. The neutron has the same kind of gluon C. Its valence quark content differs from the proton, but it's still a baryon bound by the strong interaction. Its lack of overall electric charge does not make its interior calm. The quarks inside carry electric charge, and their movements contribute to measurable properties. Gluons bind them and create the same kind of energetic internal world. The neutron's mass is slightly different from the proton's mass, and that small difference has enormous consequences for the universe. It helps determine how neutrons behave outside nuclei, how nuclei are stable, and how nuclear reactions unfold. A tiny difference at the baryon level can shape chemistry, stars, and the history of matter. The gluon C also helps explain why the proton is not just a little knot of electric charge. The proton has a size, but not a hard surface. It has internal distributions of charge and magnetism. When electrons scatter from protons, they reveal that the proton's charge is spread out according to a pattern. But that pattern is not the outline of a solid shell. It is a distribution arising from quarks, gluons, and quantum motion. Measuring the proton's size has even led to puzzles, because different methods have sometimes given slightly different values. Such puzzles are useful. They remind us that the proton, familiar as it is, still challenges our most precise understanding. There is another reason the gluon C matters. It is central to the spin of the proton. Spin is a quantum property, not exactly ordinary rotation, though the name invites that image. Physicists once hoped the proton's spin could be explained mainly by the spins of its quarks. Experiments showed that quark spin accounts for only part of the total. Gluons contribute, and so does the orbital motion of quarks and gluons inside the proton. The proton's spin is a collective result. Even the simple statement that the proton has spin hides a long internal accounting problem. The proton is common, stable, and essential, but it is not finished as a subject of research. It continues to behave like a small locked box that occasionally rattles in a new way. When people hear that particles are made of other particles, they often imagine the story as a sequence of smaller and smaller solid things. Molecules are made of atoms. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks. It sounds like a set of nesting dolls. But the gluon C interrupts that picture. It shows that the deepest levels of matter are not just smaller dolls hidden inside larger dolls. They are fields, interactions, energy, constraints, and patterns. The baryon is not a final doll open to reveal three smaller dolls. It is a field system whose identity depends on how quarks and gluons are bound. This does not make the simpler story useless. For many purposes, it is perfectly fine to say that protons and neutrons are made of quarks. In a classroom, this is the correct first step. In explaining the periodic table, one does not need to discuss gluons' self-interaction over breakfast, unless breakfast has already taken a very unusual turn. But when asking what a baryon is really made of, we must include the gluons. Otherwise, we leave out the very thing that holds the baryon together and supplies much of its mass. It would be like describing a living body by listing bones and forgetting muscles, blood, nerves, and the fact that the person is currently trying to find their keys. The strong force is so powerful inside baryons that it creates stability from chaos. Quarks cannot be isolated. Gluons interact with themselves. Temporary pairs appear and disappear. Momentum and spin are shared in complicated ways. Yet the proton remains the proton. The neutron remains the neutron, until conditions allow it to decay. The baryon has a stable public identity despite a crowded private life. This is a recurring theme in physics. Large-scale order often arises from small-scale activity. Temperature arises from molecular motion. Pressure arises from particles colliding. Sound arises from coordinated vibrations. In a baryon, mass and identity arise from the strong field binding quarks into a persistent state. The phrase gluon C should not make us imagine water sloshing inside a tiny container. There is no little liquid inside a proton. The C is a metaphor for the abundant, fluctuating, shared field activity. It is a way to say that gluons are not rare visitors, they are deeply involved. At high energies, their presence dominates aspects of the proton structure. In collider experiments, gluons inside protons play a major role in producing new particles when protons are smashed together. The proton beams in a collider are not just streams of simple positive balls, they are streams of composite gluon-rich objects. When they collide at high speed, it is often the quarks and gluons inside them that undergo the hard interactions. The outer label says proton, but the actual collision can involve its inner constituents. This is why particle physics experiments with protons are both powerful and complicated. Protons are easy to accelerate because they are charged and stable, but they are not elementary. When two protons collide, the event is messy because each proton contains many possible interacting patterns. Out of that mess, physicists reconstruct patterns, look for rare events, and compare results with predictions. The gluon sea is part of both the challenge and the opportunity. It makes the proton a rich source of interactions, but also makes the final debris complex. It is a little like trying to study two pocket watches by hurling them together at nearly the speed of light, and then learning clockmaking from the glittering spray. Remarkably, with enough detectors, statistics, and patience, it works. The gluon sea also connects the smallest scales to cosmic history. In the early universe, before protons and neutrons formed, matter existed in an extremely hot state, where quarks and gluons were not confined into ordinary baryons in the same way. This state is often called a quark-gluon plasma. As the universe expanded and cooled, quarks and gluons became confined into hadrons, including baryons. So every proton in ordinary matter is a survivor of a transition in the early universe, when the free-flowing quark and gluon state gave way to the bound particles that could later form nuclei. The protons in your body are not merely old, they are relics of a time when the universe itself was too hot for ordinary nuclei, too hot for atoms, and far too hot for anyone to complain about the weather. In laboratories, physicists can briefly recreate tiny droplets of such extreme matter by colliding heavy nuclei at enormous energies. These experiments do not make ordinary protons open like boxes in a permanent way, but they do help study the behaviour of strongly interacting matter under extreme conditions. They show that quarks and gluons can form a hot, dense medium with surprising properties. This research helps connect baryons to the broader story of the strong force, from the inside of a proton to the first moments of cosmic history, and perhaps to the cause of neutron stars. For our purpose, the main point is steady and clear. A baryon is held together by gluons and the strong field they belong to. The three valence quarks define the baryon's basic identity, but the gluon sea gives the interior its binding, energy, complexity, and much of its mass. The baryon is not a simple object with a force added between parts. It is a strongly interacting system, and the force is part of the system's substance. This is why a proton can be so durable while being so active inside. This is why quarks cannot be pulled out like seeds. This is why ordinary matter has mass rooted in something much deeper than little hard grains. The closer we look, the less matter resembles the solid picture our hands suggest, yet that does not make the world flimsy. It makes it more remarkable. Solidity emerges from atoms. Atomic identity emerges from nuclei. Nuclei emerge from protons and neutrons. Protons and neutrons emerge from quarks held in the gluon sea. The whole chain holds because the laws at each level produce stable behaviour. The table beside you may seem calm, but its calmness depends on an extraordinary amount of hidden order. Deep inside its atoms, baryons are held together by one of the strongest and strangest interactions in nature, and most of their mass is the mass of that hidden binding. Once that is understood, the next question becomes almost unavoidable. If the individual quarks inside a proton are so light, and if the gluon field supplies so much of the mass, then what does it really mean to say that a proton is mostly energy rather than stuff? That question takes us from the sea that binds a baryon into the deeper issue of mass itself, and why the familiar weight of the world comes not from tiny pieces sitting still, but from fields moving, confining, and holding themselves together in the small, bright engine room of matter. By now, the proton has stopped looking like a tiny solid bead, and has started to look more like a tightly organised storm. It has three valence quarks, yes, but those quarks are not sitting quietly inside it, like raisins in a very small bun. They are moving, interacting, exchanging gluons, surrounded by a sea of field activity, and confined in a region so tiny that ordinary pictures begin to fail, almost as soon as we draw them. And this brings us to one of the strangest facts in all of physics. The proton, one of the main building blocks of ordinary matter, gets most of its mass not from the masses of the quarks inside it, but from the energy of the strong interaction. That sentence is easy to say, but it asks us to loosen our grip on a very old intuition. We're used to thinking of mass as stuff, A stone has mass because it contains stone stuff. A loaf of bread has mass because it contains bread stuff, along with perhaps a little regret if you were meant to save half for tomorrow. A person has mass because the body's made of tissues, bones, water, proteins, minerals, and all the other material ingredients of life. At ordinary scales, this way of thinking works well enough. If you add more material, the object usually becomes heavier. If you remove material, it becomes lighter. A full suitcase is heavier than an empty one, especially if you packed as though moving permanently to a climate that has not yet been invented. But when we follow matter downward into the proton, that simple idea stops being enough. The proton has mass. It resists being accelerated. It contributes to the weight of atoms. It helps make your body, your chair, the floor, the planet, and the stars heavy in the ordinary sense. But if we ask where that mass comes from, the answer is not simply from three little chunks of material inside. The quarks inside a proton have their own masses, but those masses are small compared with the mass of the proton as a whole. If you could somehow add the masses of the three valence quarks as if they were little grocery items placed on a scale, you would account for only a small fraction of the proton's mass. The rest comes from the energy of the quarks moving, the gluons binding, the fields fluctuating, and the strong interaction holding everything together. So the proton is not mostly stuff in the old sense. It is mostly energy organized into a stable particle. That does not make it unreal. It does not make it ghostly. It does not mean matter is secretly imaginary, like an overdue bill you choose not to open. It means that what we call matter is deeper and more active than the everyday word stuff suggests. The proton is real because it behaves consistently, because it has measurable properties, because it forms atoms, because it can be studied and predicted and used in technology. But its reality is not the reality of a miniature stone. It is the reality of a bound field system whose energy gives it mass. The connection between mass and energy is one of the great discoveries of modern physics. We do not need to write the famous equation to understand its message in words. Energy can contribute to mass. A system with energy stored inside it can weigh more than the same system without that energy. In ordinary life, this effect is usually too small to notice. A hot cup of tea has slightly more mass than the same cup of tea when cold because heat is energy. The difference is far too tiny for your kitchen scale to notice, even if your kitchen scale already has a flair for drama. But in the proton, the energy of the strong force is not a tiny correction. It is most of the story. The proton's mass is largely the mass of internal energy. This is why the strong interaction matters so much. It is not merely a force keeping quarks from drifting apart. It creates an energetic environment. Quarks are confined in a small region. Because they are confined, they are restless. Their motion contributes energy. The gluon field between and around them contributes energy. Gluons themselves carry the charge of the strong force, so they interact with one another, making the field even more active. Temporary quark and antiquark pairs arise in the sea. The whole proton is a compact churning system. The mass we measure from outside is the mass of that system, not just the mass of three quarks listed like ingredients on a packet. There is a useful comparison with a wound spring, though as always with comparisons, it should not be pushed too far. A spring that is compressed or stretched contains stored energy. That energy can affect the system. In the proton, the strong field is not a little metal spring, but the idea that binding and motion can store energy is helpful. The energy is not optional. You cannot take the proton, remove the energy of the strong field, and still have the same proton but lighter. The proton exists as the bound state. Its identity depends on the energy of confinement. It is not three quarks plus a bit of decoration. It is three valence quarks and a whole strong field structure. The energy is part of the object. This also helps explain why the proton can be stable even while its inside is active. In daily life, when something is very active, we often expect it to be unstable. A shaking table may collapse. A boiling pot may spill. A room full of excited toddlers may produce a situation best described by insurance paperwork. But in physics, activity does not always mean instability. A stable system can contain motion. The planets move around the sun, yet the solar system can remain orderly over long periods. Electrons in atoms occupy quantum states rather than falling into the nucleus, even though their behavior is not like little planets orbiting neatly. The proton contains intense internal motion, but the strong interaction organizes that motion into a durable bound state. It is stable because the rules allow a low energy configuration for the whole system, not because the parts are frozen. The word energy can sometimes sound vague because we use it loosely in everyday speech. We say someone has energy when they are lively. We say a room has good energy when we like the lamps and the chairs are not too aggressive. In physics, energy is much more precise. It is a measurable property of systems. It appears in motion, fields, radiation, heat, mass, and binding. It can change form, but it is conserved in the sense that the total accounting remains consistent. Inside a proton, energy is not a mood. It is the physical content of motion and fields. The proton's mass is the outside measurement of that internal energy arranged as a stable particle. Now this raises a gentle but important question. If mass can come from energy, why do we say the proton is made of quarks at all? Why not say it is made of energy? The answer is that both statements need context. Energy is not a substance floating around by itself like invisible soup. Energy is a property of things and fields. The proton has quark fields and gluon fields arranged in a particular bound state. The energy belongs to that arrangement. Saying the proton is made of energy alone can become misleading because it leaves out the structure. A song is made of sound, but that does not tell you the melody, the rhythm, or why one song makes you calm and another makes you wonder who approved the trumpet section. The proton is made of quarks and gluons, but its mass is mostly energy from their motion and interaction. The structure and the energy belong together. The valence quarks give the proton its defining pattern. 2 up quarks and 1 down quark set the proton's identity and overall electric charge. But the mass is not mostly the little rest masses of those quarks. The gluons and the sea of activity are not minor extras. They contribute heavily to the energy budget. In high-energy experiments, when physicists probe the proton, they find that momentum is shared among quarks, antiquarks, and gluons. The valence quarks do not carry everything. The gluons can carry a great deal. This supports the picture of the proton as a dynamic system, rather than a simple 3-part object. It is worth thinking about how strange this is for ordinary matter. Most of the mass of the atoms in your body comes from protons and neutrons. Most of the mass of protons and neutrons comes from strong interaction energy. Therefore, much of your body's mass and the mass of every ordinary object around you comes from confined energy in baryons. Your hand, resting quietly, is heavy because of energy bound inside countless protons and neutrons. Your bones have weight because of energetic fields in baryons. A mountain has weight because the nuclei in its atoms are filled with protons and neutrons whose mass is mostly strong force energy. Matter, at its foundation, is not little hard stuff all the way down. It is energy in stable patterns. This can feel almost too strange, but it is a very practical strangeness. It is not philosophical decoration. It is what allows calculations and experiments to agree. Physicists can use the theory of quarks and gluons to compute the masses of protons, neutrons, and other baryons with impressive success. These calculations are difficult because the strong force is strong in this regime, but by using large numerical methods, researchers can start from the rules of quantum chromodynamics and recover the masses of hadrons. In plain language, when the rules for quarks and gluons are allowed to run, the mass of the proton emerges. It is not placed by hand like a label on a jar. It arises from the dynamics of the fields. The neutron follows the same story. It is slightly heavier than the proton, though the difference is small. That small difference matters enormously. A free neutron can decay, while a free proton appears stable. Inside atomic nuclei, neutrons can be stable depending on the arrangement. The balance of proton and neutron masses affects nuclear stability. The formation of elements and the behaviour of matter in the early universe. Even tiny mass differences between baryons can shape the cosmic inventory. The reason ordinary atoms exist in their particular forms depends on details that seem, from far away, almost absurdly small. Physics is full of these small differences with large consequences. It is rather like discovering that the entire dinner party depends on whether someone put the teaspoons in the correct drawer. When we say a proton is mostly energy, we should also be careful not to imagine a little glowing ball of energy inside it. Energy is not sitting there as a separate fluid. The energy is in the fields, the motion, the confinement, the interactions. The proton is a stable excitation of quantum fields. That phrase may sound technical, but it means the proton is a real pattern in the underlying fields of nature. The quark fields and gluon fields are excited in a way that produces a particle with definite properties. The particle can move through space, it can bind with electrons to form hydrogen, it can join other baryons in nuclei, it can be detected, it can scatter, it can endure. Its mass is the mass of that field pattern. One of the most helpful shifts is to stop asking what tiny stuff fills the proton and start asking what stable process makes the proton. In everyday life, an object can be made of material that remains basically the same whether assembled or not. The wood in a table is still wood if you remove one plank. The screws remain screws. In a proton, the ingredients do not have that kind of separate household existence. Quarks are not found alone. Gluons do not sit apart as bits of glue in a drawer. The proton exists because of the combined behaviour. The strong force does not merely attach parts together. It creates the conditions in which the parts are what they are inside the baryon. This is partly why the mass of a composite particle is not always just the sum of the masses of its constituents. In physics, the mass of a bound system includes the energy of binding and motion. Sometimes binding energy reduces the mass of a system compared with separated parts, as in atomic nuclei where the bound nucleus has slightly less mass than its separated protons and neutrons. That missing mass corresponds to energy released when the nucleus forms. In the proton, the situation is different because the quarks cannot be separated as free pieces in the same way, and the energy of confinement and motion is enormous compared with the quark masses. The main lesson is that mass belongs to the whole system. It is not always a simple inventory of parts. The phrase mostly energy can also make people wonder whether matter and energy are interchangeable in a loose way. In physics, they are related, but not identical in every context. Matter is usually used for particles with mass and structure, things like atoms, protons, neutrons, electrons, and so on. Energy is a property that matter and fields can carry. Light carries energy. Motion carries energy. Fields carry energy. A proton has mass because of the energy of its internal fields and particles. This does not mean the proton is just a vague blob that could be anything. It has specific quantum numbers, specific charges, specific interactions. Energy without structure would not give you a proton. It would give you a statement too broad to be useful, like saying a cake is made of ingredients, temperature, and hope. True perhaps, but not enough to bake one. The strong interaction gives the proton its special kind of structure. Quarks have colour charge. Gluons carry colour charge. The whole proton is colour neutral. The fields inside arrange themselves so that no colour charge is exposed to the outside. This colour neutrality is why the proton can exist as a particle we observe freely, while the quarks inside cannot be isolated. The energy of the gluon field is tied to this confinement. Try to pull quarks apart, and the field energy grows until new particles form. The proton's mass is bound up with that same behaviour. It is a small, contained result of a force that refuses to behave like a simple, weakening pull. There is something almost humorous about the proton's public modesty. From the outside, it presents itself as a small, positive particle, very dependable, very useful, happy to sit at the centre of a hydrogen atom and get on with the day. Inside, it's a roaring quantum conversation of quarks and gluons, with most of its mass arising from activity rather than from the bare mass of its ingredients. It is like someone who appears calm in a meeting while internally remembering every awkward thing they have said since childhood. The surface is composed, the inside is busy, yet in the proton's case the busyness is not a flaw, it is the source of its existence. This idea also changes how we think about the visible universe. Stars, planets, dust clouds, and living bodies are often called baryonic matter because they are made largely from baryons. Dark matter, whatever it is, does not seem to be ordinary baryonic matter. The visible structures we know are built from protons and neutrons, and those protons and neutrons are mostly strong field energy. So when we look at a galaxy through a telescope, the light comes from stars made of plasma, atoms, nuclei, and baryons. The glowing matter we see is ultimately tied to confined energy in protons and neutrons. The universe is not merely filled with objects, it is filled with stable arrangements of fields that can form objects. In stars, this hidden energy plays another role. Nuclear fusion releases energy by changing the binding arrangements of nuclei. Stars do not burn like logs in a fireplace. They shine because nuclear reactions transform matter in ways that release energy. The details depend on the masses and bindings of protons, neutrons, and nuclei. The strong force is central to this. It holds nuclei together, shapes which reactions are possible, and helps determine how much energy is released. Every bit of sunlight that warms a morning window is connected, through a long chain of processes, to the behaviour of baryons and the forces that bind them. A cup of tea warmed by sunlight is therefore, in a very practical way, borrowing comfort from nuclear physics. Which is a polite thing for tea to do. At the level of the proton itself, there is no tiny engine burning fuel. The energy that contributes to the proton's mass is not being spent away as the proton sits there. A stable proton is not like a battery slowly draining. Its mass energy is part of its existence. Unless the proton participates in a reaction or collision that transforms it, it remains a proton. The energy is locked into the structure. This is why protons can last so long. They're energetic inside, but not unstable in the ordinary sense. Their internal energy is arranged in a permitted stable state. This is also why particle collisions can create new particles. If enough energy is concentrated in a collision, it can appear as mass in new particles, provided the rules of conservation allow it. In high-energy accelerators, protons are smashed together, and the energy of their motion can produce heavy particles that did not exist before the collision. This is another expression of the relationship between energy and mass. The proton itself already demonstrates the same principle internally. Energy in fields and motion contributes to mass. In collisions, energy can be reorganized into new massive particles. Nature is very strict in its bookkeeping, but quite creative in its accounting categories. The idea that mass can arise from energy also prevents us from thinking of the Higgs field as the whole story of mass. The Higgs field is important. It gives fundamental particles like quarks and electrons their intrinsic masses through their interaction with it. But the mass of ordinary matter is not mostly the direct Higgs, given mass of the up and down quarks and electrons. Since most ordinary mass is in protons and neutrons, and most of proton and neutron mass comes from strong interaction energy. The Higgs field is only part of the full story of the mass we feel in everyday objects. Without the Higgs field, the quark masses would change, and the structure of matter could be very different. But the heavy lifting, in ordinary matter as we know it, is largely done by the strong force energy inside baryons. If mass were a stage production, the Higgs field would be an essential cast member, but the Gluons would be carrying a surprising amount of scenery backstage. This distinction is important because popular explanations sometimes simplify mass too much. They say particles get mass from the Higgs field, which is true for certain fundamental particles, but then people may assume that the mass of everything around them comes directly from that mechanism. The proton teaches a more interesting lesson. Fundamental masses matter, but composite masses can be dominated by energy. Most of the mass of a proton emerges from the dynamics of quantum chromodynamics, so the weight of ordinary matter is not just handed to particles by one field. It is built through the interactions that create stable bound systems. The proton is therefore a kind of lesson in emergence. Emergence means that a system has properties that arise from the collective behaviour of its parts and rules, rather than being obvious from the parts alone. A single water molecule is not wet in the everyday sense, but many water molecules together can make a liquid with wetness, waves, droplets, and puddles that socks always find eventually. A single air molecule does not have a temperature in the same way a gas does, but a collection of molecules does. In the proton, the mass, spin, size, and other properties arise from quarks and gluons interacting. The whole particle is more than a list of ingredients, it is a collective quantum state. This does not mean mystery replaces explanation. Emergence in physics is not a shrug. It is a way of saying that the correct explanation lives at the level of interactions and collective behaviour. We can study it, we can measure it, we can calculate it, though sometimes with difficulty. The proton's mass is mysterious only if we expect it to come from tiny solid pieces. Once we accept that fields carry energy, and energy contributes to mass, the proton becomes less like a paradox, and more like a remarkable example of the rules doing their work. Still, the feeling of strangeness is worth keeping. It keeps us honest. The world feels solid because atoms resist compression, because electrons and electromagnetic forces create surfaces, because nuclei provide mass and identity. But the mass at the centre of those atoms comes largely from something not solid in the everyday sense. It comes from quark and gluon energy inside baryons. So the familiar world rests on unfamiliar foundations. A wooden desk is not secretly an illusion, but its mass is rooted in confined field energy. A stone is not less real because its weight comes from quantum dynamics. If anything, it is more interesting than a simple stone had any right to be. When you lift your hand, the effort you feel is connected to the mass of the tissues and bones, which is connected to the atoms in them, which is connected to the nuclei, which is connected to protons and neutrons, which is connected to the energy of the strong force. Your muscles use chemical energy to move matter, whose mass is mostly nuclear and baryonic in origin. The ordinary act of reaching for a glass involves layers of physics stacked quietly beneath awareness. No wonder we get tired. We are asking biological machinery to move organised strong field energy around the room, and yet all of this happens without drama in daily life. The proton does not need us to understand it in order to keep existing. It does not become lighter when ignored or heavier when admired. Though that would make science lectures more dangerous, it simply continues, a stable result of quarks and gluons, carrying its mass as the outward sign of inward energy. In atoms, in molecules, in living cells, in planets and stars, the proton does its work quietly. So when we ask why a proton is mostly energy, not stuff, the answer is that the stuff inside is not enough. The quarks matter, but their bare masses are only a small part of the total. The strong field binds them, confines them, fills the interior with gluons and fluctuating activity, and creates a large amount of energy in a small space. That energy contributes to the proton's mass. The proton is a stable bundle of quark and gluon dynamics. It is not empty. It is not solid in the old way. It is a persistent pattern of fields, and that pattern is heavy. This prepares us for another strange part of the story. The strong force does not use electric charge, and it does not follow the familiar rules of attraction and repulsion that we learn from magnets or static electricity. It has its own kind of charge, called colour charge, with rules so odd that physicists had to build an entirely new theory to describe them. Colour charge explains why quarks combine as they do, why baryons must hide their strong charge from the outside world, and why the interior of a proton is full of gluons rather than held together by a simple invisible string. To understand what a baryon is made of, we have to understand not just the pieces and the energy, but the strange rulebook that tells the pieces how they are allowed to exist together. The strange rulebook begins with a word that sounds far more visual than it really is: colour. In ordinary life, colour belongs to sunsets, curtains, traffic lights, socks that should not have gone into the wash together, and the mysterious shade of soup that appears when several leftovers are combined without a clear plan. But in particle physics, colour means something else entirely. It is not something you can see. It is not red, green, or blue in the way paint is red, leaves are green, or a clear sky can look blue on a good day. Colour charge is the name physicists give to the kind of charge that quarks carry under the strong force. It is the strong force version of electric charge, though the comparison is only a starting point, because colour charge follows rules that are much stranger than ordinary electricity. Electric charge is familiar enough, at least in its everyday effects. Opposite electric charges attract, like charges repel. Electrons carry negative charge. Protons carry positive charge. This helps atoms form, chemistry happen, and balloons cling awkwardly to walls after being rubbed on jumpers. Electromagnetism can act over long distances, and because positive and negative charges can cancel, many objects around us are electrically neutral overall. The rules are subtle in detail, but the basic idea is not too hard to carry around. Electric charge comes in two kinds, positive and negative, and their behaviour gives us a large part of the world we experience directly. Colour charge is not like that. It comes in three types, and because physicists have a long tradition of choosing names that are either very plain or slightly whimsical, those three types are often called red, green, and blue. Their corresponding anticolours belong to antiquarks. Again, these are labels, not actual visual shades. A red quark is not a tiny red speck. A green quark is not a microscopic pea. A blue quark is not a little drop of paint. These words were chosen because three different colour labels can combine in a way that is roughly analogous to visible colours combining into a neutral result. But the analogy should be treated gently. It is a naming system for a mathematical property, not a miniature art class inside the Proton. The reason colour charge matters is that quarks feel the strong force because they carry it. A quark has electric charge, but it also has colour charge. The electric charge helps determine how quarks contribute to the overall charge of a proton or neutron. The colour charge determines how quarks interact through the strong force, and because the strong force is the force that holds baryons together, colour charge is not a minor detail. It is the rule that decides how quarks may combine, why they cannot be found alone, and why the inside of a proton is such a crowded, active place. The most important rule is this. The particles we observe freely in the world must be colour neutral. That means their colour charge is balanced so that no net colour charge is exposed from the outside. In a baryon, three quarks combine their colours into a neutral whole. In a meson, a quark and an antiquark combine colour and anticolour into a neutral whole. This is why a proton can exist as an independent particle, while one isolated quark cannot. The proton is colour neutral overall. Its quarks are not individually neutral, but their combined colour state is. The outside world does not see exposed colour charge. It sees a proton with an ordinary electric charge and other measurable properties, but its strong charge is hidden inside, balanced. This idea of hidden colour is one of the major differences between quarks and the particles we meet more directly. An electron can exist freely. A photon can travel across the universe. A proton can exist freely because it is colour neutral. But a single quark carrying colour charge by itself does not appear as a free particle under ordinary conditions. No matter how hard physicists have looked, they do not find lone quarks drifting through detectors like tiny independent billiard balls. Quarks are confined. They are always found inside colour-neutral combinations. This is not simply because our tools are clumsy. It is a deep feature of the strong interaction. The force carrier of the strong interaction is the gluon. In electromagnetism, the force carrier is the photon. Photons carry energy and momentum, and they can be emitted and absorbed by electrically charged particles. But photons do not themselves carry electric charge. That means, in ordinary electromagnetism, photons do not directly pull on each other in the same way charged particles do. Gluons are different. Gluons carry color charge. They do not merely pass messages between quarks, they also feel the strong force themselves. They can interact with other gluons. This makes the strong force self-interacting, tangled, and far more complicated than a simple exchange between two particles. That self-interaction is one of the reasons the strong force behaves so strangely. Imagine trying to understand a conversation in which every messenger delivers messages, edits the messages, argues with other messengers, creates more messengers, and occasionally rearranges the room. That is not a perfect description, because gluons are not little people with clipboards, but it captures the sense of why the strong force becomes so rich. The field is not passive, it is active. Inside a baryon, the gluon field is constantly involved, and because gluons interact with gluons, the interior becomes a dense sea of strong field activity. This also helps explain why the strong force has such different behaviour at different distances. When quarks are very close together, they can behave almost as if they are less strongly tied. This property has a technical name, but the basic idea is simple enough in words. At very short distances, the strong interaction becomes easier to handle, and quarks inside a high-energy collision can sometimes act like nearly free particles for a brief moment. This was a surprising discovery because one might expect a strong force to always be strong in the same way, but nature chose a more interesting arrangement. At tiny separations, the force becomes less intense in a certain calculable sense. At larger separations, it becomes confining. That is the opposite of what our everyday force intuition might expect. With gravity, the pull between objects weakens with distance. With ordinary electric forces, the influence between charges also weakens as separation grows. Move things far enough apart and the force becomes smaller. With quarks, trying to separate them does not free them in a simple way. The energy in the strong field grows, and before a quark can escape alone, the energy can create new quark and antiquark pairs. The result is not one lonely quark, but new color-neutral particles. Nature pays the energy bill by making more hadrons rather than allowing a bare color charge to wander off by itself. This is confinement, and it is one of the defining facts of quark physics. It is also why a baryon is not something we can dismantle like a clock. You can take apart a bicycle and lay the chain, wheel, handlebars, and slightly confusing leftover washer on the floor. You cannot take apart a proton and lay 3 free quarks beside the gluons. If you strike a proton hard enough, you can reveal its internal structure, and you can produce sprays of new particles, but you do not obtain a single isolated quark sitting politely in a detector. The strong force turns that attempt into more bound particles. It is as though the universe has a strict policy that color charge must always be hidden from public view. The rule of color neutrality explains the basic architecture of baryons. 3 quarks can combine so that their color charges balance. This does not mean every baryon literally contains 1 red quark, 1 green quark, and 1 blue quark in a fixed ordinary sense, like 3 colored buttons sewn onto a coat. Quantum mechanics is more subtle. The baryon's color state is a combination, a balanced arrangement in which the whole is neutral. The colors of individual quarks are not fixed labels that remain unchanged like name tags at a conference. Quarks exchange gluons, and those exchanges can change their color charges, while preserving the overall neutrality of the baryon. The proton remains color neutral, but the internal color bookkeeping is dynamic. This is another place where the word made can mislead us. A baryon is made of 3 valence quarks, but the color charge of those quarks is constantly involved in gluon exchange. The whole particle is not just 3 quarks with 3 permanent colors. It is a quantum color singlet, meaning a balanced state with no net color charge. We do not need the technical language in the narration, but the idea matters. Color neutrality is not a paint mixture frozen in place. It is a rule satisfied by the whole quantum state. The baryon hides its color through a balanced internal arrangement that remains consistent even as the internal activity changes. Because gluons carry color, they also help create the sea inside the baryon. A gluon emitted by one quark can be absorbed by another, but gluons can also split or interact with other gluons. The number of gluons in the proton is not fixed like the number of chairs around a table. At high energies, the proton can appear packed with gluons, especially when probed very finely. The 3 valence quarks define the main identity, but the gluon population and the C quarks are part of the full physical picture. This is why color charge is not just a label on quarks. It creates the entire internal life of the baryon. There is also a reason the strong force is strong only over very short distances in ordinary matter. Color confinement means the strong charge is hidden inside color-neutral particles. Outside a proton or neutron, the direct color force does not extend outward in a simple long-range way, because the color charge is neutralized. However, there is a leftover effect of the strong force between protons and neutrons inside atomic nuclei. This residual nuclear force is what helps bind nuclei together. It is not the same as having exposed color charge reaching across large distances. It is more like the remaining effect of deeper, strong interactions inside color-neutral particles. This residual force acts over very short ranges, which is why nuclei are compact and why the strong nuclear force does not pull on your spoon from across the table in any noticeable way. The spoon has enough going on already. This separation between the fundamental strong interaction and the residual nuclear force can be confusing, but it is helpful. Inside a proton, quarks are bound by gluons through color charge. Between protons and neutrons in a nucleus, there is a short-range attraction that arises from the strong interaction, but acts between color-neutral particles. In older nuclear models, this force was described through the exchange of particles called mesons. Modern understanding connects it to the underlying quark and gluon theory, but at the nuclear level it is often useful to work with protons and neutrons as whole particles. Again, physics uses different levels of description depending on the question. At one level, protons and neutrons are the actors. At a deeper level, quarks and gluons are the actors. At an even broader level, stars and galaxies do not usually ask to see anyone's color charge identification. The theory that describes color charge and the strong force is quantum chromodynamics. The name sounds almost musical, but it is built from straightforward pieces. Quantum because it belongs to quantum field theory. Chromo because it concerns color charge. Dynamics because it describes how the fields and particles behave. It is one of the central parts of the standard model of particle physics. It explains why quarks bind into hadrons, why gluons matter, why color charge must be neutralized in observable particles, and why the proton is such an energetic object inside. Quantum chromodynamics has a peculiar personality. In some high-energy situations, it becomes easier to calculate because the force becomes weaker at very short distances. In the low-energy world of protons, neutrons and nuclei, it becomes difficult because the force is strong and confinement dominates. This is why some problems involving the strong force require enormous numerical simulations. Physicists place the theory on a lattice, a kind of grid for space and time, and use powerful computers to calculate how quark and gluon fields behave. These calculations have become one of the major tools for understanding hadron masses and properties. It is not a matter of drawing 3 quarks and guessing. It is a deep computational problem, the kind that makes supercomputers hum warmly in buildings where everyone has strong opinions about cooling systems. One of the triumphs of this theory is that it explains how most of the proton's mass can arise from strong interaction energy. The color fields and gluon dynamics contribute enormously. The quark masses alone are not enough. The strong force is not just a binding agent, but an energy-generating structure in the sense that the bound system contains large internal energy. The proton's mass emerges from the color dynamics, so color charge is connected not only to why the proton holds together, but also to why it is heavy. Without color charge and gluons, the baryon as we know it would not exist. The color rules also help organize the larger family of hadrons. Baryons are made from 3 valence quarks in color-neutral combinations. Mesons are made from a quark and an antiquark in colour-neutral combinations. For a long time, those were the main hadron categories discussed in basic particle physics. More recently, experiments have found evidence for more exotic hadrons, such as particles whose structures can be described with 4 or 5 quark components. These are still colour-neutral overall. The rule does not say only 2 or 3 quark combinations can ever exist. It says that free particles must be colour-neutral. Nature can build more complicated neutral arrangements, though many are unstable and short-lived. The proton and neutron remain special because they are the stable baryons that build ordinary matter. This rule of neutrality has a pleasing strictness. It means that no matter how complex the inside becomes, the outside must satisfy the hidden colour balance. A proton can contain valence quarks, gluons, and C quarks, but as a whole it carries no net colour charge. A neutron does the same. A pion, a kind of meson, also does the same. The strong force allows complexity, but it demands balance before a particle can appear freely. It is a bit like a household where chaos may reign in the cupboards, but the front hallway must look presentable before guests arrive. There is another subtle point. Colour charge does not replace electric charge. Quarks carry both. An up quark has one kind of electric charge and a colour charge. A down quark has a different electric charge and a colour charge. The electric charges combine to give the proton a positive charge, or the neutron no overall charge. The colour charges combine to give both particles colour neutrality. These are separate layers of bookkeeping. The proton is electrically positive but colour neutral. The neutron is electrically neutral and colour neutral. If that sounds like a lot for such small particles to manage, it is. Fortunately, particles do not have to manage it consciously. The laws do the bookkeeping. Because baryons are colour neutral, the strong interaction is hidden from direct everyday experience. You do not notice colour charge in a chair. You do not feel gluons pulling when you open a door. What you feel at the surface of objects is mostly electromagnetic interaction between electrons and atoms. Yet the mass and nuclear stability behind those atoms depend on the strong force. Colour charge is therefore one of the most important invisible properties in nature. It is not visible like ordinary colour, not familiar like electric charge, and not long-range like gravity, but it quietly makes the stable nuclei of the world possible. It also explains why particle physics cannot always rely on common-sense pictures. We like forces that act between objects separated in space, like magnets pulling or gravity attracting. The strong force at the quark level is a quantum field interaction with self-interacting carriers, confinement, scale-dependent behaviour, and hidden charges that must combine into neutral states. It is not simply stronger electromagnetism, it has its own rules. If electromagnetism is a polite letter sent across distance, the strong force is more like a crowded kitchen in which the cooks, the recipes, the pans, and the smoke alarm are all interacting at once. Useful, intense, and not something you want to describe with only one sentence. The reason colour charge must be hidden is tied to the energy of the field. A lone colour charge would involve a field configuration whose energy does not behave like the field around a lone electric charge. The strong field tends to confine colour. This is why observable particles are colour neutral. In experiments, when quarks or gluons are produced in high-energy events, they quickly transform into jets of colour-neutral hadrons. This process is called hadronization. The details are complex, but the visible result is that detectors see sprays of particles, not free quarks or free gluons. Even when the collision begins with quark and gluon interactions, the final world respects colour neutrality. This is one reason the strong force is both hidden and obvious. Hidden because we never see free colour charge. Obvious because the particles produced in high-energy collisions reveal its effect everywhere. The jets, the particle patterns, the masses of hadrons, the stability of nuclei, the behaviour of neutron stars, the early universe transition from quark-gluon plasma to hadrons, all of these carry the fingerprints of colour charge. It is invisible in daily life, but loud in the right experiments. For baryons, colour charge is the reason 3 quarks can become 1 particle. The quarks are not held together because they are tiny objects that happen to like company. They are bound because the strong interaction through colour charge and gluons creates permitted neutral states. A baryon is one of those states. Its identity depends on which flavours of quarks are present, such as up and down for protons and neutrons, but its ability to exist freely depends on colour neutrality. The quarks inside may exchange colours through gluons, but the whole remains balanced. The proton's positive electric charge can be seen from outside, but its colour charge is hidden. That is part of why a proton can sit calmly in a hydrogen atom, rather than dragging the entire strong force visibly into chemistry. This balance also helps us understand why the proton is robust. The strong interaction binds the quarks tightly, and because the proton is the lightest baryon with its conserved properties, it has no easy way to decay under known ordinary processes. The neutron, slightly heavier, can decay when free, but inside nuclei it may be stabilized by the surrounding nuclear arrangement. Other baryons, made with heavier quarks or different combinations, usually decay quickly into lighter particles. Colour charge makes baryons possible, but flavour and mass determine which baryons last. Nature has many baryon recipes, but only a few are suitable for building long-term furniture. If this feels like a lot of rule-making for a universe that often looks simple, that is because simplicity at our scale is built on strictness below. The chair does not need to know about colour charge, because every proton and neutron inside it has already obeyed the rules. The atoms are stable because their nuclei are stable. The nuclei are stable because protons and neutrons interact through nuclear forces. The protons and neutrons exist because quarks are confined in colour, neutral baryons. Every level hides the complexity of the one beneath it, allowing the next level to behave in a simpler way. This is how physics gives us an ordinary world from extraordinary rules. A useful way to think of colour charge is as a hidden organising principle. It is not something added to quarks after the fact. It is one of their fundamental properties. It determines how they couple to gluons. It determines why gluons self-interact. It determines why only certain combinations become observable particles. It determines why the proton is full of field energy. It determines why quarks remain confined. The word colour may sound gentle, but the physics behind it is fierce. And yet fierce does not mean chaotic without order. The strong force is governed by precise laws. Its behaviour may be difficult to calculate in some regimes, but it is not random. The proton is reproducible. A proton here and a proton in a distant galaxy follow the same rules. The same colour charge principles hold in a laboratory accelerator, in the heart of a star, and inside the atoms of a sleepy listener's blanket. There is comfort in that. The deep rules are strange, but they are consistent. The universe may have chosen a complicated instruction manual, but at least it keeps using the same one. So the strange rules of the strong force tell us why a baryon is not simply 3 quarks placed side by side. The quarks carry colour charge. Gluons carry colour charge too, and because of that they interact with each other. The whole baryon must be colour neutral. Quarks cannot be isolated because colour charge is confined. Pulling on a quark creates new hadrons rather than a free quark. The gluon field supplies much of the baryon's mass through internal energy. The proton and neutron are stable or nearly stable not because they are simple, but because these rules organise their complexity into lasting particles. With that rulebook in place, we can begin to see the baryon family more clearly. The proton and neutron are the ones we live with, but they are not alone. Change the flavours of the quarks, and other baryons appear, some strange, some heavier, some fleeting, some formed only in accelerators or extreme astrophysical environments. The same colour rules hold them together, but their different quark contents give them different masses, lifetimes and personalities. Ordinary matter is built mostly from the 2 quiet relatives we know best. Yet beyond them is a larger family of baryons, a particle clan that reveals just how many ways the strong force can make 3 quarks behave as one. Once the strong force has been allowed into the room, the proton and neutron no longer seem like lonely particles with simple labels. they become the two most familiar members of a much larger family, a family held together by the same hidden rules of colour charge, gluons, confinement, and quark flavour. The proton is the one we meet most often because it defines the elements and can survive on its own for extraordinary lengths of time. The neutron is its close companion, similar in size and mass, quieter in electric charge, less stable when left alone, but absolutely essential inside atomic nuclei. Together, they make the ordinary cores of atoms, but they are not the whole story. Beyond them are other baryons, heavier relatives with stranger ingredients, usually brief lives, and names that sound as if they have wandered in from a mythological birdwatching guide. Hyperons, deltas, sigmas, lambdas, ghis, omegas. The baryon family is larger than the small pair that builds tables and teacups, and by looking at that family we learn why protons and neutrons are special rather than simply common. The neutron is a good place to begin because it is familiar and unfamiliar at the same time. It lives in the nucleus of nearly every atom around you, except for the simplest hydrogen atom, which has only a proton at its centre. It contributes mass. It helps stabilise nuclei. It changes isotopes. It makes the difference between one version of an element and another. Yet because it carries no overall electric charge, it does not announce itself as loudly as the proton. A proton attracts electrons because of its positive charge. A neutron does not. It sits there, electrically neutral from the outside, and perhaps for that reason it can feel less dramatic. But this calm outer appearance is misleading. The neutron is not empty, not featureless, and not simple. Inside it are quarks and gluons, just as in the proton, arranged so that the total electric charge balances to zero. A neutron contains one up valence quark and two down valence quarks. The charges of those quarks add up to no net electric charge, which is why the neutron is neutral overall. But those internal charges are still there. They move. They contribute to the neutron's magnetic behaviour. They participate in the strong interaction. The neutron is neutral in the way a carefully balanced account is neutral, not in the way a blank page is neutral. There's plenty going on inside. It simply cancels from the outside in one important respect. This is a useful reminder for physics and also, occasionally, for human conversation. Quiet does not always mean empty. The free neutron is unstable. If a neutron is removed from a nucleus and left alone, it will decay after a while into other particles. This is one of the major differences between the neutron and the proton. The proton seems to be stable on timescales far longer than the age of the universe, as far as experiments can tell. The neutron, outside a nucleus, has a limited lifetime. Inside a nucleus, however, a neutron can be stable because the surrounding nuclear environment changes the energy balance. This sounds a bit like a particle that behaves better with company, which is not the worst comparison. A free neutron is not in its most comfortable long-term arrangement, but in the right nucleus it can remain part of a stable structure. This fact matters enormously. If neutrons could not be stable inside nuclei, the periodic table would be drastically poorer. Many elements need neutrons to hold their nuclei together. Protons repel one another electrically, so as nuclei grow larger, they require neutrons to help supply strong nuclear attraction without adding more positive charge. The neutron is therefore a quiet stabilizer. It allows many proton-rich nuclei to exist without flying apart. It helps create the diversity of elements. Without neutrons, the universe would have a much thinner chemistry, and chemistry is rather important if one enjoys planets, oceans, cells, baking, or the continued existence of soup. The neutron also plays a central role in nuclear transformations. In certain forms of radioactive decay, a neutron can turn into a proton, changing one element into another. In other processes, protons can be converted into neutrons under the right conditions. These transformations are governed by another fundamental interaction, the weak force. So the neutron sits at a crossroads. It is a baryon bound internally by the strong force, part of nuclei bound by residual strong interactions, and able under some circumstances to change identity through the weak force. It is not merely a neutral lump in the nucleus, it is one of the central working pieces of nuclear physics. The proton and neutron are sometimes grouped together under the name Nucleons, because they are the particles that make up ordinary atomic nuclei. This is a useful nuclear physics word. It treats the proton and neutron as two versions of a similar particle, which makes sense because they are close relatives. They have similar masses, similar sizes, and similar strong interactions. Their main obvious difference is electric charge. This closeness is one reason they can form nuclei together so effectively, but from the deeper quark point of view, they are different combinations of up and down quarks. The proton has 2 up valence quarks and 1 down valence quark. The neutron has 1 up valence quark and 2 down valence quarks. Change 1 quark flavor and you move from one particle to the other. This idea that baryons are classified by their quark content opens the door to the broader family. Up and down quarks are the lightest quarks, and they form the stable baryons of ordinary matter. But nature contains other quark flavors too. There is the strange quark, heavier than the up and down quarks. There are charm, bottom and top quarks, heavier still. When baryons contain one or more strange quarks, they're often called hyperons. Hyperons are baryons, but they are not the baryons that build ordinary atoms. They are heavier and unstable. They can be created in high-energy particle collisions, and they may appear in extreme astrophysical environments. But in the calm matter around us, they do not last. If a hyperon appeared in your cup of tea, it would be gone far faster than you could decide whether to be impressed or concerned. The first hyperons were discovered in cosmic ray studies and particle experiments, at a time when physicists were finding more and more particles and trying to make sense of them. These particles seemed unusual because some of them were produced through strong interactions but decayed much more slowly than they expected, for particles governed only by the strong force. This odd behaviour led to the concept of strangeness, a property associated with the strange quark. The name strange was chosen because the particles really did behave strangely compared with what physicists anticipated. It is one of those cases where the scientific name is both technical and emotionally honest. A hyperon is therefore a baryon with a strange quark in its valence structure. The lambda baryon, for example, contains one strange quark along with up and down quarks. Sigma baryons also contain strange quarks in different arrangements. She baryons contain even more strangeness. The omega- baryon, historically very important, contains 3 strange quarks. Its discovery was a triumph for the quark model, because the model predicted its existence and properties before it was observed. That is one of the moments scientists love most. A pattern is proposed, an empty space appears in the pattern, the theory says something should be there, and then experiment finds it. It is rather like noticing a missing biscuit from a plate, and correctly predicting not only that someone took it, but which cupboard they are hiding beside. Hyperons show that baryons are not limited to the proton and neutron. The 3-quark rule can build many combinations, change the quark flavors, and the mass changes. The charge changes, the lifetime changes, the possible decay paths change. The strong force still binds the quarks through color charge, and the baryon remains color neutral overall, but the flavor content gives each baryon its personality. Some are heavier versions of familiar patterns. Some have electric charges different from the proton or neutron. Some decay through the weak force because they contain strange quarks and cannot remain stable as ordinary matter. There are also baryons that do not contain strange quarks, but are still heavier and unstable. The delta baryons, for instance, are excited relatives of the proton and neutron. They are made from up and down quarks, but arranged in higher energy states. They decay quickly, often into a nucleon and a pion. This reminds us that a baryon is not defined only by which quarks are present. The internal energy state matters too. Just as an atom can have electrons in excited states without becoming a different element, a baryon can have excited states that are heavier and unstable. The proton is the lowest stable arrangement for its quark content. push the system into a more energetic configuration, and it can become a short-lived excited baryon before decaying. This is where the baryon family begins to resemble not a simple list of particles, but a whole spectrum of possible strong force arrangements. The quarks are ingredients, but the field configuration, spin arrangement, energy state, and flavor content all matter. A baryon can be in a ground state or an excited state. It can contain light quarks or heavier quarks. It can be stable or fleeting. It can carry different electric charges. Yet all baryons share the underlying structure of being color-neutral states built from 3 valence quarks, along with the gluon C and quantum activity that always accompany them. The existence of heavier baryons helps confirm the deeper rules. If protons and neutrons were the only baryons, one might wonder whether they were special isolated objects. But when experiments reveal whole families of baryons with patterns in mass, charge, and decay behavior, it becomes clear that a deeper classification is at work. The Quark model explains these patterns. Quantum chromodynamics explains why quarks bind, and why color neutrality is required. The baryon family is therefore evidence that matter has an underlying grammar. The proton and neutron are not random syllables. They are common words formed by the same grammar that can also form rarer, heavier, shorter, lived words. Some baryons contain charm or bottom quarks. These are heavier flavors, and the baryons that contain them are produced in high-energy environments. They decay quickly through the weak interaction. Top quarks, however, decay so rapidly that they do not have time to form ordinary bound baryons in the usual way. This detail shows that not every quark flavor participates equally in long-lived composite matter. The up and down quarks are light enough and stable enough in their arrangements to form the enduring nucleons. Strange quarks can form hyperons, but those hyperons decay. Charm and bottom quarks form even heavier, short-lived baryons. The top quark barely waits around long enough to join the family dinner before leaving. This hierarchy of quark masses shapes the universe. If the up and down quarks were much heavier, protons and neutrons would be different. If the strange quark were lighter, hyperons might be more common in stable matter. If particle masses and force strengths were altered, the building blocks of atoms could change radically. The familiar dominance of protons and neutrons is not just because they happen to arrive first, it is because they occupy a stable low-energy role in the particle family. They are the baryons that last long enough to build worlds. The neutron's place in this family is especially interesting because it is nearly stable, but not quite. A free neutron decays, but a neutron bound inside a stable nucleus can endure. This conditional stability allows nuclei to have rich structure. It also affects the early universe. In the first minutes after the Big Bang, the balance between protons and neutrons helped determine how much hydrogen and helium formed. Neutrons that survived long enough could combine with protons in the first nuclei. If the neutron lifetime or mass difference between proton and neutron had been very different, the early chemical composition of the universe would have shifted. Later stars would have inherited a different starting mixture. A tiny property of one baryon helped shape the cosmic inventory. Neutrons also become dramatically important in the lives and deaths of stars. In the core of a massive star, matter can become so compressed that electrons and protons combine to form neutrons. When the star collapses, it may leave behind a neutron star, an object containing matter at densities far beyond ordinary nuclei. A neutron star is not simply one enormous atomic nucleus, though that comparison is often tempting. Its structure is more complicated, with layers and extreme states of matter. But neutrons and neutron-rich nuclear matter dominate the story. Under such crushing conditions, other baryons may appear too. Some theories suggest that hyperons could form in the cores of neutron stars when densities become high enough. This is an active area of research because the presence of hyperons would affect how stiff or soft the matter is, and therefore how massive a neutron star can be. This connects the baryon family to astrophysics. Hyperons are not only laboratory curiosities, they may matter inside some of the densest stars in the universe. If extreme pressure makes it energetically favourable to create strange baryons, then the interior of a neutron star might contain a richer mixture of baryons than ordinary matter does. Understanding that possibility requires nuclear physics, particle physics, and astronomical observation to speak to one another. A particle that lives for a fraction of a moment in an accelerator may also be part of the hidden recipe inside a collapsed star. The universe enjoys reusing its ingredients in rather unexpected kitchens. In particle accelerators, baryons are studied by creating them in collisions and tracking how they decay. Because many baryons are unstable, physicists often infer their existence from the particles they produce as they break apart. Detectors record tracks, energies, and decay patterns. From these clues, researchers reconstruct the short-lived baryon that must have been present. This is not unlike identifying a guest at a party only from the crumbs, footprints, and slightly embarrassed witnesses left behind. It takes careful analysis, but it can reveal particles that exist for times far too short to observe directly in an ordinary sense. The decays of hyperons and other baryons teach physicists about the weak force, symmetry, and the structure of matter. They show how quark flavors can change. They test the predictions of particle theory. They help refine our understanding of how quarks are arranged inside hadrons. Even though protons and neutrons are the baryons most relevant to daily life, the unstable relatives are scientifically precious because they reveal the rules more fully. A family is easier to understand when you meet more than one relative. The proton alone is impressive, but the larger baryon family shows the pattern behind it. There is also a conservation rule associated with baryons. In ordinary particle interactions, a quantity called baryon number is conserved. Baryons carry it, antibaryons carry the opposite, and the total accounting remains balanced in known processes. This rule helps explain why protons do not simply disappear in ordinary reactions, and why creating a baryon often involves creating an antibaryon as well, unless another baryon is already present to balance the account. The details are technical, but the idea is simple. Nature keeps track of baryonic identity. This conservation is part of what makes ordinary matter persistent. If baryon number were easily violated, the universe could behave very differently. Some theories beyond the standard model allow proton decay, which would violate this conservation, but experiments have not observed it. So far, protons appear extraordinarily faithful to existence. The existence of antimatter adds another layer. For every baryon, there can be an antibaryon made from antiquarks. An antiproton is the antimatter counterpart of the proton. An antineutron is the counterpart of the neutron. Antibaryons have opposite electric charges, where applicable and opposite baryon number, but they are governed by the same underlying physics. When baryons and antibaryons meet, they can annihilate, converting their mass energy into other particles. In the early universe, matter and antimatter were likely created in nearly equal amounts, yet today, the visible universe is dominated by matter. Why there is more baryonic matter than antibaryonic matter is one of the deep questions in cosmology. The baryon family therefore touches not only the structure of matter, but also the mystery of why there is something like our kind of matter left at all. This matter-antimatter imbalance is not needed to understand what a proton is made of, but it shows how broad the baryon story becomes. Baryons are the particles that build the visible world, and the universe contains far more baryons than antibaryons today. That asymmetry allowed stars, planets, and chemistry to form rather than everything annihilating into radiation. Somewhere in the early history of the cosmos, the rules produced a tiny preference for matter over antimatter, or allowed such a preference to survive. That small imbalance became everything familiar. The baryons in your body are part of that leftover majority. They are the matter that did not vanish in the ancient accounting. The proton, then, is not merely one particle among many. It is the long-lived survivor at the base of ordinary matter. The neutron is its nuclear partner, stable in company, transformative when alone, essential for the diversity of nuclei. Hyperons are heavier relatives, usually strange in the technical sense and brief in lifetime, but important for revealing the quark model, and perhaps for understanding extreme stars. Excited baryons show that even the same quark ingredients can form different energy states. Heavy flavoured baryons show how charm and bottom quarks can join the pattern for a moment before decaying. Antibaryons show that the family has a mirror side. Together, all of them make baryons not a single object, but a category of strong force structures. It is useful to return to the quiet room around you. The stable matter nearby is not made from hyperons or charm baryons. Those particles are too unstable for ordinary furniture, which is probably for the best. Your room is built mainly from electrons, protons and neutrons, with protons and neutrons carrying most of the mass. But the reason protons and neutrons are special becomes clearer only after seeing the larger family. They are the durable low-energy relatives. They are the baryons that nature can use for long-term construction. The rest of the family appears under special conditions, giving physicists clues about the rules, then fades into lighter particles. This fading is not failure. It is how unstable particles reveal themselves. Many baryons are too massive to remain as they are. They decay into lighter hadrons and other particles, following conservation laws and force rules. Their short lives are part of the story. Stability in physics is not guaranteed by being real. A particle can be real and fleeting. It can exist for a tiny fraction of a second and still have definite properties, still be measured, still fit into the family pattern. The proton is unusual because it lasts. The neutron lasts in nuclei. Hyperons live briefly. Each lifetime tells us something about what transformations are allowed. There is a calm lesson here about ordinary matter. The world is built not from every possible particle, but from the ones that can persist under everyday conditions. Nature has a vast menu, but stable matter orders very simply. Up quarks, down quarks, electrons, gluons binding the quarks, photons mediating electromagnetism, and a few other quiet background ingredients depending on the context. Most of the heavier particles are not part of daily matter because they decay. They are important not because they fill your desk, but because they show what the laws allow when enough energy is available. They are glimpses of the full rulebook. The baryon family therefore helps answer the original question more honestly. What is a baryon made of? It is made from 3 valance quarks arranged into a color-neutral state, surrounded and bound by gluons and C quarks, with mass arising largely from strong interaction energy, but which baryon it is depends on which quark flavors are present and how the internal state is arranged. A proton is one particular stable arrangement, a neutron is another, nearly stable and essential in nuclei. A hyperon is a heavier arrangement involving strange quarks. Other baryons involve heavier quarks or excited energy states. They are all variations on the same strong force theme. And from here, the story begins to widen again. We have gone inside the baryon, then looked across its family. But baryons are not only particles in a catalogue, they are the material from which the visible universe is built. They gather into nuclei, atoms, gas clouds, stars, planets, and bodies. They participate in the birth and death of stars. They shape the matter we can see, touch, and measure with ordinary instruments. To understand baryons fully, we have to step outward from the proton and neutron and watch what they do on cosmic scales, where these tiny, strongly bound particles become the substance of galaxies, stellar cores, rocky worlds, and the quiet atoms listening along with us in the dark. Now that we have met the baryon family, it is worth stepping back from the crowded interior of the proton and letting the view widen. We have spent time inside tiny particles, among quarks, gluons, colour charge, confinement, and the restless strong force. That is a very small place to spend an evening, even by the standards of physics. But baryons are not only interesting because of what happens inside them, they matter because of what they become when nature uses them in large numbers. A single proton is a particle. A great cloud of protons and neutrons can become a star. A dense collection of baryons can become a planet. A patient arrangement of them can become a tree, a hand, a cup of tea, a sleeping cat, or a listener somewhere in the world wondering how something so small ended up being responsible for so much. This is one of the strange pleasures of physics. the same object can belong to two very different stories at once. A proton is a quantum object bound by gluons, but it is also part of hydrogen. Hydrogen is a chemical element, but it is also the fuel of stars. Stars are astronomical objects, but they are also furnaces that change baryons into new nuclear arrangements. Those new arrangements later become planets and bodies. So when we speak about baryons, we are not only speaking about particles in accelerators or diagrams in textbooks. We are speaking about the visible material history of the universe. Baryons are the kind of matter that can clump, shine, burn, cool, freeze, melt, grow, decay, and eventually sit quietly in a room listening to science for sleep. The word baryonic matter is often used by cosmologists to describe ordinary matter, the matter made from protons and neutrons, along with electrons to form atoms. Ordinary here does not mean boring, it only means familiar. Baryonic matter includes almost everything you see directly through telescopes and almost everything you touch in daily life. It includes stars, glowing gas clouds, planets, moons, comets, dust, oceans, rocks, living cells, and all the slightly mysterious things at the back of the refrigerator. It is the matter of chemistry and light. It absorbs radiation, emits radiation, forms atoms, and participates in the rich physical processes that create visible structure. If something shines by its own light, reflects light, blocks light, or can be held in your hand without requiring a particle detector and a very nervous safety committee, it is probably baryonic matter. And yet baryonic matter is not most of the universe's matter. That is one of the great surprises of modern cosmology. The matter we know best, the matter of stars and bodies, appears to be only a fraction of the total matter content. Much of the matter in the universe seems to be dark matter, which does not behave like ordinary baryonic matter. It does not appear to form atoms, shine, or interact strongly with light. We know it mainly through gravity. But baryonic matter is still the matter that makes the visible universe rich. Dark matter may provide much of the gravitational scaffolding that helps galaxies form, but baryons are the material that cools, collapses, ignites, and becomes luminous. If dark matter is part of the invisible framework, baryonic matter is the part that turns on the lamps. In the early universe, before atoms existed, before stars, before galaxies, matter was in a hot, dense state. At first, conditions were too extreme for protons and neutrons to behave as ordinary stable particles in the way they do now. As the universe expanded and cooled, quarks and gluons became confined into hadrons, including baryons. Protons and neutrons emerged from that cooling state. Later, when the universe cooled further, some of those protons and neutrons formed the first light nuclei. Hydrogen nuclei, which are single protons, were abundant. Helium nuclei also formed, along with small traces of other light nuclei. But the early universe did not produce large amounts of heavy elements. It made the simplest nuclear ingredients in great abundance, then handed the next stages of creation over to stars. Stars are baryonic matter under gravity's patient command. A star begins as a large cloud of gas, mostly hydrogen and helium, spread through space. Gravity pulls the cloud inward. As it collapses, it heats. The center becomes denser and hotter until nuclear fusion can begin. Fusion is not ordinary burning. A candle burns because molecules react chemically with oxygen. A star shines because nuclei are transformed. In stars like the Sun, hydrogen nuclei are ultimately converted into helium through a chain of reactions. The details are complex, but the broad idea is clear enough. Protons, which are baryons, are rearranged into more tightly bound nuclei, and energy is released. That energy pushes outward as radiation and pressure, balancing gravity for much of the star's life. The sunlight that reaches Earth began in nuclear processes involving baryons in the Sun's core. It took a long journey outward through the solar material and then across space before warming your face, feeding plants, stirring weather, and making curtains fade in that one patch near the window. The light feels gentle when it lands on a quiet morning, but its origin is nuclear. It is connected to protons undergoing transformations in a star. Baryons are not just heavy particles in atoms. In stars, they are active participants in the production of light. The calm glow of the sun is the visible sign of matter being rearranged at nuclear depth. As stars age, they change what baryons are doing inside them. A star's life depends strongly on its mass. Smaller stars burn slowly and can last for very long times. More massive stars live faster and more dramatically because their cores become hot enough to fuse heavier elements in later stages. Helium can be fused into carbon and oxygen. In massive stars, further stages can build neon, magnesium, silicon, sulfur, and eventually iron group elements. Each stage is another way baryons are reorganized into new nuclei. The protons and neutrons are not being created from nothing in these ordinary stellar fusion steps. They are being rearranged into nuclei with different binding energies. The star is a great baryonic workshop, taking simple nuclei and building more complex ones under pressure and heat. The elements in your body were not all made in the same place or the same event. Hydrogen in you is ancient, much of it dating back to the early universe. Carbon, oxygen, nitrogen, calcium, phosphorus, iron, and many other elements were forged in stars or in violent stellar events. Some heavy elements are made in supernova explosions. Others are made in collisions involving neutron stars, where neutron-rich matter can create heavy nuclei through rapid processes. The full story of element formation is a grand cosmic supply chain, with stars, explosions, stellar winds and mergers all playing different roles. It is not exactly a tidy factory. It is more like the universe running several furnaces, a few catastrophes, and a recycling service with no customer support line. Baryons are central to that recycling. When a massive star dies, it can eject newly formed elements into space. Those elements mix with interstellar gas. Later, new stars and planets form from enriched clouds. The atoms in Earth were gathered from such material. The nuclei in those atoms contain protons and neutrons, baryons that have passed through cosmic history. Some of the baryons in you may have once been inside a star. Others may have drifted through cold interstellar gas for ages. Others may have been part of rock, ocean, air, plant, animal, or dust before becoming part of your body. The baryons themselves are extremely durable. The arrangements change, but the protons often persist through immense spans of time. This gives a literal physical meaning to the idea that we are connected to the stars. It is not just a nice phrase for a poster above a bed, though it does work rather well there. The heavier elements in your body were made through astrophysical processes. The carbon in your cells, the oxygen in your water, the calcium in your bones, the iron in your blood, all depend on nuclear histories involving baryons. Your body is not made from freshly invented matter. It is assembled from old particles in new arrangements. You are a temporary organisation of very ancient ingredients. This is not meant to sound grand in a theatrical way. It is simply how the material world works. The universe is economical. It reuses. Galaxies are where baryons gather into visible structures on enormous scales. A galaxy contains stars, gas, dust, planets, and often a central black hole, all embedded in a larger gravitational environment that includes dark matter. The baryons are the glowing and cooling matter. Gas clouds collapse, stars form, massive stars explode and enrich the gas. New generations of stars form from that enriched material. Planets condense from disks around young stars. On at least one planet, chemistry became biology, and biology eventually developed the habit of asking what baryons are really made of while trying to fall asleep. The baryons in a galaxy do not simply sit still. They flow through cycles. Gas falls into galaxies from surrounding space. Stars form from cold, dense gas. Stellar winds and explosions push gas back out. Some gas becomes hot and diffuse. Some cools again. Dust grains form and are destroyed. Elements mix. Over billions of years, a galaxy becomes a changing ecosystem of baryonic matter. The stars are only one part of it. Between the stars is the interstellar medium, a mixture of gas, plasma, molecules, dust, magnetic fields, radiation and cosmic rays. It is not empty space. It is thin by human standards, but rich by astronomical standards. In that space, baryons are not arranged as solid objects but as gas and plasma, waiting for gravity, pressure, cooling and turbulence to decide what happens next. In the early universe, baryonic matter could not form atoms immediately because it was too hot. Electrons could not settle around nuclei while radiation was constantly knocking them away. Much later, when the universe cooled enough, electrons combined with nuclei and neutral atoms formed. This allowed light to travel more freely through space. That ancient light is still observed today as a faint microwave glow filling the universe. It carries information about the early distribution of matter, including baryonic matter. Tiny variations in that early pattern eventually grew into galaxies and clusters. The baryons followed gravitational wells shaped largely by dark matter, then cooled and formed the structures we can see. So the visible universe is a later flowering of small early differences, with baryons becoming the luminous part of cosmic structure. Within galaxies, baryons can live in very different conditions. In a star's core, they are in hot, dense plasma and nuclei undergoing fusion. In a cold molecular cloud, they may be in molecules drifting at low temperatures, shielded from harsh radiation. In a planet's crust, they are locked in minerals. In an ocean, they are arranged in water molecules and dissolved salts. In a living cell, they are part of proteins, fats, sugars, nucleic acids, membranes, and countless molecular machines. The same basic baryonic matter can become plasma, gas, liquid, solid, and life. That variety does not come because baryons change their basic nature at every step. It comes because protons and neutrons form nuclei, nuclei form atoms, atoms form molecules, and molecules form structures across many scales. This layered structure is important. A proton inside a carbon nucleus is not thinking about the tree it helps build. A neutron inside oxygen is not aware that it may be in a molecule of water in a leaf. Physics does not require awareness at lower levels. It requires consistent rules. Because baryons behave reliably, atoms can behave reliably. Because atoms behave reliably, chemistry can become rich. Because chemistry is rich, biology can become possible. Complexity is built by stacking reliable layers, not by asking each particle to understand the final result. This is fortunate. If every proton in your body needed to know your plans for tomorrow, getting out of bed would involve a committee meeting at the subatomic level. The baryons in you are mostly found in atomic nuclei. The mass of your body comes largely from protons and neutrons. Electrons are essential for chemistry, but they contribute very little to total mass compared with nuclei. Your body's shape, texture, warmth, and chemistry depend on electromagnetic interactions among atoms and molecules, but the weight of your body is mainly baryonic. The nuclei are heavy because protons and neutrons are heavy, and those protons and neutrons are heavy mostly because of strong interaction energy inside them. So in a very direct way, your physical weight is connected to gluon fields in baryons. The bathroom scale, that small square device of judgment, is responding to gravity pulling on mass that is mostly strong force energy arranged in protons and neutrons. It never explains this, of course. It simply gives a number and lets you handle the philosophy yourself. Every breath involves baryons changing arrangements. Oxygen molecules enter your lungs. Atoms bind and unbind in biochemical reactions. Carbon dioxide leaves your body. Food is broken down and rebuilt. Water moves through tissues. Minerals become part of bones. Iron in hemoglobin helps transport oxygen. At the chemical level, electrons are rearranged. At the nuclear level, the baryons mostly remain the same. The protons and neutrons are carried from one molecule to another, from air to blood to cell and back out into the world. Life is not constantly making new baryons. It is borrowing and rearranging them. Your body is a temporary pattern in a circulating stream of matter. This is a grounding idea. The atoms in you are not permanently yours. Over time, many are replaced through breathing, eating, drinking, shedding, healing, and metabolism. Matter enters, becomes part of you for a while, and leaves. The Baryons continue onward into other systems. Some may become part of another person, a plant, a cloud, a river, a stone, or a quiet layer of soil. Identity at the biological level is a pattern maintained through change. The Baryons are the material passing through. You're not a fixed pile of particles. You're an organised process that continually exchanges matter with the world. This is not mystical. It is biology resting on physics. In planets, baryons take on long, lasting geological roles. Earth's rocks are made of atoms with nuclei built from protons and neutrons. The elements in minerals determine hardness, melting point, crystal structure, and chemical behaviour. Radioactive isotopes inside Earth release heat as their unstable nuclei decay. That heat helps drive geological activity over long times. The planet's interior, crust, oceans, atmosphere, and magnetic field are all part of the story of baryonic matter under gravity, heat, pressure, and chemistry. The same protons and neutrons that form stars also form granite, salt, clay, snow, and the metal in a teaspoon. Nature is very good at making different things from the same basic cast. In the most extreme stars, baryons are pushed into conditions far beyond anything on Earth. A white dwarf is supported by quantum pressure from electrons, with nuclei packed densely in matter that is no longer ordinary solid or gas. A neutron star is even more extreme. Their matter is compressed so intensely that protons and electrons can combine to form neutrons, and the star becomes dominated by neutron-rich matter. The density is astonishing. A small amount of neutron star material would have an enormous mass. Though removing such material is not recommended and would present several practical difficulties, including the fact that it would not remain polite outside the star. Inside neutron stars, baryons may be packed so closely that new forms of matter appear. Hyperons may form. Quark matter may exist in some cores, though this remains uncertain. These objects turn baryon physics into astrophysics at its most intense. When neutron stars collide, they can create some of the heaviest elements in the universe. In such mergers, neutron-rich matter is flung outward, and rapid nuclear processes build heavy nuclei. Gold, platinum, and other heavy elements may be produced in these events. The ring on a finger, the metal in electronics, the heavy elements in Earth's crust, some of these may trace back to violent cosmic collisions involving baryonic matter under extreme gravity. It is strange to think that something as calm as jewellery may have a history involving neutron stars. But the universe has never been especially concerned with matching origins to current appearances. A peaceful object can have a dramatic past. Baryons also help shape the large-scale appearance of galaxies, because they can lose energy by radiating light. Dark matter, as far as we know, does not cool in the same way. Baryonic gas can radiate energy away, collapse further, and form disks, stars, and dense structures. This cooling ability makes baryons the active visible material in galaxy formation. They respond to gravity, but they also collide, heat, cool, ionize, recombine, and form complex phases. The glowing spiral arms of a galaxy, the pinkish emission from star-forming regions, the dark lanes of dust, the blue light of young stars and the red light of old ones, all are expressions of baryonic matter, doing what baryonic matter can do. The cosmic web, the large-scale arrangement of matter across the universe, contains baryons too. Not all baryons are locked in stars or galaxies. Many are in diffuse gas between galaxies, in warm and hot forms that can be difficult to detect. Astronomers study these hidden baryons through absorption lines, emissions and interactions with background light. This is a reminder that even ordinary matter can be elusive when spread thinly across enormous distances. Baryonic matter is familiar in our hands, but on cosmic scales much of it is faint, hot, diffuse, and hard to count. The universe hides even its ordinary ingredients with admirable commitment. When we return from those scales to a single person, the connection can feel almost too large to hold in mind. The baryons in your body are part of the same matter category as the gas in nebulae, the plasma in stars, the crust of planets, and the dense material in neutron stars. The difference is arrangement. In you, baryons are organized into nuclei, atoms, molecules, cells, tissues, organs, and a nervous system capable of wondering about its own ingredients. That is not a separate kind of matter from the universe. It is the universe arranged into a temporary living structure. The proton in a cell and the proton in interstellar hydrogen are the same kind of particle. The local story is different, but the underlying physics is shared. There is comfort in that shared physics. A proton does not behave differently because it is in a laboratory, a star, or your bloodstream. Its environment changes what it can participate in, but its basic properties are consistent. This consistency lets science connect tiny experiments on Earth to processes in distant galaxies. When physicists study baryons in accelerators, they are not studying something unrelated to astronomy. They are studying the particles that make visible cosmic matter. When astronomers study stars, they are watching baryonic matter under extreme conditions. When biologists study cells, they are studying one elaborate arrangement of atoms whose nuclei contain baryons. The sciences are not separate islands. They are different ways of walking around the same physical world. The fact that baryons form only a minority of the total matter in the universe can make ordinary matter sound small. But small in cosmic accounting does not mean unimportant. Baryons are the matter that cools into planets and ignites into stars. They are the matter that creates spectra, chemistry, minerals, oceans, atmospheres, and organisms. They are the matter that can form mirrors and eyes, telescopes and hands, questions and notebooks. Dark matter may dominate gravitational mass, but baryons dominate the visible complexity we know directly. The universe may be mostly something else, but the part that became us is baryonic, and that part is astonishingly inventive. It is also worth noting that baryons are not forever locked into familiar forms. In stars, protons can be transformed through nuclear reactions. In radioactive decay, neutrons and protons can change under the weak interaction. In high-energy collisions, baryons can be created and destroyed with antibaryons, as long as the conservation rules are satisfied. In black holes, matter crosses horizons, and its familiar particle identity becomes part of a deeper gravitational mystery. The baryons that build ordinary things are stable enough to make worlds, but under extreme conditions they can participate in transformations that remind us matter is not fixed in one form for all time. Even so, for the purposes of everyday existence, baryons are wonderfully dependable. The protons in your atoms do not decay during breakfast. The neutrons in stable nuclei do not wander off during a nap. The nuclei in your body remain nuclei through the ordinary chemistry of life. This reliability is what allows complexity to persist. A universe where baryons constantly changed without stable rules would not support chemistry as we know it. Stable baryons are the quiet promise beneath every material object. They say in effect the centre will hold, at least long enough for atoms to become interesting. So baryons in stars, galaxies, and you are not three separate topics, they are one continuous story across scale. In the early universe, quarks and gluons became confined into baryons. In the first minutes, baryons formed light nuclei. In galaxies, baryonic gas collapsed into stars. In stars, nuclei fused into heavier elements. In stellar deaths and collisions, those elements were scattered and enriched. In planetary systems, baryonic matter cooled into rocks, oceans, air, and chemistry. In living bodies, baryons became part of cells and thought. And in this quiet moment, some arrangement of baryons has become you listening, breathing, perhaps getting sleepier, while other baryons nearby make up the room, the air, the device, and whatever object you named earlier when we began. The question of what a baryon is made of therefore has two directions. Inward it leads to quarks, gluons, colour charge, confinement, and energy. Outward it leads to nuclei, atoms, stars, galaxies, planets, and life. Both directions are necessary. If we only go inward, we may miss why baryons matter. If we only go outward, we may miss the strange machinery that lets them exist. The proton is a tiny object, but it links quantum field theory to sunlight. The neutron is a neutral baryon, but it links quark structure to the periodic table. Hyperons are unstable relatives, but they may link particle physics to neutron star interiors. Baryons are bridges, from the smallest rulebook to the largest visible structures. And that brings us close to the final form of the answer, though not by ending the thought too quickly. A baryon is not just three quarks. It is not just energy. It is not just a piece of ordinary matter. It is a stable or briefly stable pattern in the strong force, a colour-neutral arrangement of quarks and gluons that can become the heart of atoms or, in other forms, reveal the wider possibilities of particle physics. In stars and galaxies, baryons become luminous matter. In planets, they become geology. In living bodies, they become chemistry organised into cells. In you, they become the material basis of breath, warmth, memory, and the quiet ability to ask what matter is really made of. From here, the remaining step is to gather the pieces, gently and clearly, and answer the question as directly as the universe will allow. So what is a baryon really made of? After wandering from the heavy centres of atoms to the strange rules of colour charge, from the crowded room of quarks to the wide sweep of stars and galaxies, the answer is no longer quite as simple as the one we might have started with. It would be easy to say that a baryon is made of three quarks, and then close the book, turn off the lamp, and feel quite satisfied with ourselves. And for a first answer, that is not bad. It is far better than saying a baryon is made of mysterious tiny matter crumbs, which sounds charming but would not survive a physics exam. A baryon does have three valence quarks. A proton has two up quarks and one down quark. A neutron has a one up quark and two down quarks. Those quarks are essential. They give the baryon its identity. They help determine its electric charge, its place in the particle family, and whether it becomes the proton sitting at the heart of hydrogen, or the neutron helping stabilize heavier nuclei. But if we stop there, we leave out the most important surprise. A baryon is not just three quarks. It is three quarks inside an active strong field. It is three quarks plus gluons, C-quarks, motion, confinement, binding energy, colour charge, and all the restless quantum activity that turns a small collection of ingredients into one stable particle. It is not a tiny bag of parts. It is a pattern that holds. That word pattern may sound softer than the word particle, but in modern physics it is often closer to the truth. A particle like a proton is real. It has mass. It has charge. It can move. It can collide. It can sit inside an atom and help build the world. But it is not real in the same way a tiny grain of sand is real. If you imagine shrinking yourself down and walking around inside a proton with a little torch and a clipboard, you would not find three polished balls resting in a corner, labelled neatly for inspection. You would find no ordinary surface, no wall, no hard edge, no calm interior. You would find a strongly interacting quantum system, which is a rather formal way of saying that everything is happening at once and none of it is behaving like furniture. The quarks are not fixed in place. The gluons are not simple strings. The fields are not empty. The baryon is a small region where the rules of the strong interaction create a lasting object out of motion and energy. This is why baryons are such a good lesson in how matter really works. At everyday scales, matter feels like stuff. Solid stuff. Heavy stuff. The kind of stuff you can drop on your foot and immediately develop a strong respect for. But at the baryon level, matter is not simply little hard pieces stacked together. The proton has mass mostly because of energy inside it. The quarks have masses of their own, but those masses are only a small portion of the whole. Most of the proton's mass comes from the energy of the strong force, from the motion of quarks, from gluon fields, from confinement, and from the activity of the quantum sea inside. The ordinary weight of the visible world is therefore rooted in something deeply active. A stone is heavy not because it is made of tiny stones all the way down, but because its atoms contain nuclei, and those nuclei contain protons and neutrons, and those baryons contain strong field energy organized into stable particles. The stone is not less real because of this. If anything, it has become more impressive. It has earned its heaviness through an astonishing amount of hidden physics. The gluons are central to that hidden physics. Their name makes them sound simple, almost domestic, like something one might use to repair a broken mug. But gluons are not household glue. They are the force carriers of the strong interaction. They bind quarks together, but they also interact with each other because they carry color charge themselves. This is one of the deep reasons the strong force is so complicated. In electromagnetism, photons carry the force, but photons do not carry electric charge. In the strong interaction, gluons carry the very kind of charge they communicate. The messengers are also participants. The field is not merely a line drawn between quarks, it is an active sea. Inside a baryon, gluons fill the story so thoroughly that leaving them out would be like describing the ocean by mentioning only the fish. Color charge is the rule that keeps this sea organized. It has nothing to do with visible color, even though the labels can make it sound as though protons are hosting a very small art exhibition. Color charge is the strong force charge carried by quarks and gluons. A baryon must be color neutral overall. Its internal color charges are arranged so that no net color charge is exposed from the outside. That is why a proton can exist as a free particle, while a single quark cannot. Quarks are confined. They are never seen alone under ordinary conditions. Try to pull one out, and the strong field does not simply let it leave. Add enough energy, and new particles form instead. The universe seems to have a strict policy about color charge. It may be busy inside, but it must be balanced before it appears in public. This makes the baryon a very different kind of object from anything in daily life. If you take apart a clock, you can spread the gears and springs across a table, then wonder quietly how anyone ever expected you to put it back together. If you take apart a molecule, at least in principle, you can identify atoms. If you strip electrons from atoms, you can form ions. But if you try to take apart a proton into free quarks, you do not get 3 separate quarks on the table. You get new hadrons, new color-neutral particles. The ingredients refuse to exist alone. So a baryon is made of quarks, but in a way that cannot be separated from the force that binds them. The binding is not an accessory. It is not a string tied around the real object. It is part of the real object. This is why the phrase made of becomes slippery at very small scales. In ordinary life, made of means ingredients that can be removed and held separately. A sandwich is made of bread and filling. A wall is made of bricks. A cup is made of ceramic, glass, or metal, depending on the cup and how much confidence it has in gravity. But a baryon is made of quarks and gluons in the sense that it is a stable state of those fields. Its ingredients are not all independent little objects waiting to be counted. They are aspects of a quantum field system. The quarks are real. The gluons are real. The C quarks are real in the proper quantum sense. The energy is real, but the baryon is the whole arrangement. Its identity lives in the combination. The proton is the most familiar example, and perhaps the most important for ordinary matter. It is stable, positively charged, and able to attract electrons to form atoms. It defines elements. One proton gives hydrogen. More protons produce the rest of the periodic table. The neutron is its close relative, neutral overall, stable inside many nuclei, unstable when alone, and essential for building heavier elements. These two baryons are the heavy centers of everyday atoms. They are why atoms have most of their mass. They are why chemistry has a nuclear anchor. They are why stars have fuel and planets have substance. And yet each proton and neutron is itself a little strong force world, crowded with activity that remains hidden unless we probe deeply. Other baryons show that the proton and neutron are not isolated miracles. They are members of a larger family. Add strange quarks, and hyperons appear. Use heavier quarks, and other short-lived baryons appear. Excite the quark and gluon system, and heavier baryon states appear even with familiar ingredients. Most of these particles decay quickly. They are not the material of chairs, oceans, and bones. But they reveal the rule book. They show that baryons are a category, a way the strong interaction organizes quarks into color-neutral particles. The proton and neutron are special because they last and because they sit at the foundation of ordinary matter. They are not the only possibilities. They are the possibilities nature can build with for the long term. So the answer to our question depends on how deeply we want to listen. If we ask at the level of the particle family, a baryon is made of 3 valence quarks. If we ask at the level of the strong force, it is made of quarks bound by gluons in a color-neutral state. If we ask about its mass, it is made mostly of internal energy from motion and fields. If we ask about what fills it, we must include gluons in the sea of temporary quark and antiquark pairs. If we ask what it becomes in the universe, it becomes nuclei, atoms, stars, planets, and living bodies. Each answer is true at its own depth. None alone is enough. This layered answer can feel less satisfying than a simple one at first. We often want the universe to hand us a final bead, the smallest possible thing, the last little object from which all other objects are assembled. But baryons teach us that nature is subtler. At the deepest levels we currently understand, matter is not merely made of smaller pieces. It is made of fields and interactions. It is made of allowed states. It is made of energy organized by rules. The proton is not a little stone at the bottom of reality. It is a stable pattern in quantum fields. That may sound less solid, but it is solid enough to build worlds. In fact, it is exactly what has built them. Think again of your own body. It is made of cells. The cells are made of molecules. The molecules are made of atoms. The atoms have nuclei. The nuclei contain protons and neutrons. The protons and neutrons are baryons. Inside those baryons are quarks and gluons held by the strong force. Much of their mass is energy. The whole chain is present in you right now, not as an idea but as physical fact. You're not floating above physics. You are physics arranged into biology, memory, warmth, and perhaps a slightly heavier eyelid than a few minutes ago. Every breath moves baryonic matter in and out of your body. Every heartbeat pushes atoms whose nuclei are built from baryons. Every thought depends on chemistry, and every chemical atom is anchored by nuclei, and those nuclei depend on protons and neutrons quietly continuing to be themselves. The same is true of the room around you. The walls, floor, blankets, glass, book, lamp, wires, and air are all arrangements of atoms. Most of the mass in those atoms is baryonic. The electrons create chemistry and surfaces, but the mass sits mainly in the nuclei. The nuclei sit mainly in protons and neutrons. The protons and neutrons sit, if sit is the right word, as strong force patterns of quarks and gluons. So the stillness of a room is built on hidden restlessness. The quiet object beside you is not quiet all the way down. Inside its atoms, baryons are full of quantum motion. The world feels calm because the activity is stable, balanced, and governed by rules that do not need our attention. There is something reassuring about that. The deep interior of matter is not simple, but it is dependable. A proton in your hand behaves like a proton in a distant nebula. A neutron in a nucleus follows the same principles here as in a star. Quarks and gluons obey the same strong force rules whether they are in a laboratory detector, the heart of the sun, or the atoms of a sleeping cat. Science can move between scales because the rules remain consistent. We can study particles and accelerators and use that knowledge to understand the early universe. We can study starlight and learn about nuclear reactions. We can study atoms and infer the behavior of matter across cosmic distances. The baryon is small, but it connects many branches of physics because it sits at the meeting point of particles, nuclei, stars, and ordinary life. And maybe this is the most direct answer of all. A baryon is made of relationship as much as ingredient. The quarks matter, but their relationship through the strong force matters just as much. The gluons matter, but the way they confine and interact matters just as much. The energy matters, but the structure of that energy matters just as much. A baryon is not a heap, it is a bound state. It is not only content, but organization. It is a tiny example of one of the great themes in nature, that stable things can emerge from motion when the rules allow it. This theme appears everywhere. A wave is not a separate substance from water, but a pattern moving through it. A flame is not a solid object, but a process that holds shape, while fuel and gases change. A living body is not the same atoms forever, but an organized pattern maintained through exchange. A baryon is not exactly like any of these, but they help us soften the old idea that real must mean still and solid. The proton is real because its pattern is stable. Its quarks and gluons form a durable whole. Its properties are measurable. Its presence builds atoms. Its mass helps shape matter. The fact that it is active inside does not make it less real. It makes it a deeper kind of real than our everyday imagination first expects. So when someone asks what a baryon is really made of, the calmest answer is this. It is made of 3 valence quarks, bound by gluons through the strong force, filled with quantum field activity, and held in a color-neutral state. Its mass comes mostly from the energy of that binding and motion, not from the small masses of the quarks alone. In ordinary matter, the most important baryons are protons and neutrons, and they form the nuclei of atoms. In the wider particle family, many other baryons exist, usually heavier and short-lived. Across the universe, baryons become the visible matter of stars, gas, planets, and life. That is the answer, as plainly as the strange little universe inside matter will let us say it. But perhaps the answer also carries a gentler lesson. The world around you is not less solid because it is made from fields and energy. It is not less familiar because its foundations are strange. A cup is still a cup. A hand is still a hand. A star is still a star. Physics does not take away ordinary reality by explaining it. It adds depth beneath it. It lets the cup become atoms, the atoms become nuclei, the nuclei become baryons, and the baryons become quarks and gluons in a strong field. Then it lets the whole picture rise back up again until the cup is once more simply there, holding tea, quietly participating in the universe without making a fuss. And now, as we come back from the inner life of baryons, perhaps the room feels just slightly different. The ordinary objects nearby may seem a little heavier with meaning, though not enough to affect the furniture. The air around you is full of atoms. The device playing this voice is made from elements forged and gathered through cosmic history. Your body is a temporary living arrangement of ancient baryonic matter. Deep inside it all, protons and neutrons continue their hidden work, bound by gluons, carrying mass as organized energy, holding the centers of atoms together while the larger world dreams above them. If this quiet journey through the heart of matter has helped you unwind, or made the small things around you feel a little more interesting, I would be ever so grateful if you liked the video and subscribed. It helps this calm corner of science find other curious travelers who may enjoy drifting through physics without being startled awake by too much excitement. And if you are still awake, that is all right. You have spent the evening inside the Proton, which is a perfectly respectable place to be, provided one does not try to move in permanently. So wherever you are listening from, whatever time it is in your little part of the world, let the thoughts settle gently. The matter around you is not a dead collection of tiny blocks. It is a stable arrangement of deep activity. The baryons inside atoms are small, but they carry the history of the early universe, the fire of stars, the structure of planets, and the quiet weight of your own breathing body. A baryon is made of quarks, yes, but also of gluons, energy, confinement and rules that turn motion into matter. And in that strange, steady way, the universe has built something solid enough for you to rest in, soft enough for sleep, and deep enough to keep asking questions long after the lights go low.